Okay, we're being recorded now, and welcome to Lecture 2 of Advanced Introduction of Machine Learning. First thing I'd like to do is um, announce that our second TA is online, and our second TA is Chandrasekhar. And I think, it's actually something I can do. I can just take a quick snapshot of him, and I hope you don't get too mad at this, Chandrasekhar, but here you are. Chandrasekhar. So, isn't technology irritating? Actually, let me just put you a little bit down here. Right. Okay, there's Chandrasekhar. So he's our second TA, and he and Niraja, who is currently in my upper right corner, but that doesn't help you. In fact, I should, in the interest of equality, I should embarrass Niraja as well as Chandrasekhar as well. And there she is. So there are two TAs. Okay, sorry, Niraja. Hope you don't mind too much. If you mind, I'll delete it. Okay, so homework 1. I wanted to, before we begin, mention homework 1. So I'm still working on homework 1. It's not yet done, but the goal is to get it posted tonight or tomorrow morning. And like I said, homeworks are going to be done asynchronously with the class lectures. So it will be posted. You'll get a Canvas message about it. You'll have about a week and a half, maybe a little bit longer, probably a week and a half on this one to do it. And we have office hours this week. At least my office hours are Thursday night at 10 p.m. via Zoom, and here's the link. And then, of course, next week will be office hours. So that means you'll have 2 of my office hours, as well as next Tuesday's lecture to ask questions about the homework. Although I do recommend to everybody to start on the homework as soon as possible. And then, of course, the other thing I should probably mention is the snow. You're all not here in person, and Seattle tends to overreact, which is perhaps one way of putting it, to a little bit of snow. And being consistent with the policy of Seattle's reaction to 0.3 microns of snow, we will actually, that's not true. It's not fair to folks who live outside of Seattle. I know that a lot of people are coming from outside of Seattle, but I think it's kind of funny, like folks from Utah who have like 2 feet of snow and it's no problem, and we react heavily about a little bit of snow. But then to be fair and to be serious for a moment, I think a big part of it is the fact that we don't have the infrastructure for dealing with snow, unlike which has a fleet of snowplows, which we don't have. Okay, so what we're doing today is we're really going to be starting, after we do a review, we're going to start on logistic regression and really complexity in the bias variance trade-off. That's pretty much what we're going to be doing. Maybe, and this is really, logistic regression is more supervised learning. That's our goal. And today is the 14th. I want to acknowledge a few references that, some of this material has been drawn from. The Bishop book, the 96 version of the Bishop book is, like I said before, very good. And actually that Bishop book has a great discussion of bias variance. However, I think the lectures here are self-contained. So it should be the case based on seeing today's lecture and reading through the slides, which have been posted on the website on Canvas for a couple of days now. It should be sufficient for you to fully understand everything, hopefully. Okay, so next what we're going to do is we're going to do a bunch of review. And in this section here, by the way, somebody is shuffling stuff around. So if you're shuffling stuff around and generating noise, feel free to mute yourself, because I can hear the noise. And then I think everybody else can hear the noise as well. But obviously, if you ask a question and I don't respond, then check your mute level. And the other thing I guess I should mention here with Zoom is that, you know, there's this you supposedly have like voting things, like you can click yes, no, go slower, go faster. You can do thumbs up, thumbs down, hand clap, need a break, and away, and clear all. I guess I can do clear all. So I generally prefer it if, yes, so Tyler is saying yes to me, I guess privately. So it's a group chat. We have a group chat. So you can chat things if you want, or if you see somebody waving and I'm looking down at my notes, then feel free to group chat or something to get my attention. And somebody's clicking, say go faster. Okay, that's great. That's great feedback. Anonymously. By the way, that kind of stuff is anonymous. So that's 1 vote for go faster and no votes for go slower. So maybe I'll go a little faster. The one question was, when was homework 1 will be due? It'll be due about a week and a half after I assign it, and I'm going to try to finish it tonight after class, and if not tonight, then it'll be assigned tomorrow morning, and it'll be due about 1.5 weeks after it is assigned. So you know, I guess about 11 days after it's assigned. So that gives you an idea. Okay, a couple of other readings that I think you'll find useful. The Matrix Cookbook, some linear algebra notes from Stanford. And then I posted a write-up. I hope everybody has read the write-up on overfitting and underfitting. If you have, feel free to click yes. If you haven't, feel free to click no. But anyway, it's been posted for a while, since last week. And part of it we will be talking about that today. Okay, so this is the review section, like I said. So this is a section where we spend time reviewing last week's slides. So everything while we're in this period, these are all slides from last week. And this is the part that if you want at the end of the class to do, say, a brief summary of the whole course, what you would do is just look at these review sections and then stop the YouTube lecture at that point. So what we did last time is we kind of gave this kind of broad overview of what machine learning is, and we have these 12 different sections.
Is the screen stuck, or is it just me?
I'm sorry, say again?
Is the screen stuck? Is it like the slides are not moving, or is it just my system?
What do you see? Do you see frame 7?
I see the advanced introduction to machine learning first slide, and I didn't see the others.
Are you not seeing any of the slides?
Right, yeah. So only the first screen.
Oh my God. So in fact, we've had a lot of slides since then. So you just see, so you don't see anything else?
No, it's F158 is what it says. Advanced introduction to machine learning, that like the front.
Okay, that's not good. Let me try sharing again. Thanks for pointing that out. You did see when I posted this picture of you guys, right? So what do you see now? Could you tell me what you see?
Yeah, so now I see the opening advanced introduction to machine learning slide, and
right.
the
and what do you see now?
Yeah. It's still the first page.
Still the first page?
Yes.
And this is still the first page too?
Yeah, still the first page.
And how about now?
No, it's not moving, Professor.
Still the first page?
Yeah.
Okay, so we'll have to try something different. I don't think that's ever happened before. So, okay, what about now? What do you see now? First page?
First page.
Yeah. What about now?
Yeah, now it moved. Now it moved, second, third, yeah.
Okay.
Now it's going forward.
Yeah, I'm just doing a different screen sharing option. That's very bizarre that this is a Zoom problem then. Okay. I mean, it's unfortunate. So basically, I marked this up here, the virtual office hours. We had this slide, which we talked about this. Talked about this material that was drawn from, I mentioned several times that this is the section when you see these tick marks, these are the review. So I was kind of pointing at this stuff up here. Can you see what I'm pointing at up there? Up
yes,
top right?
yes. Now we can see everything.
Okay,
Yes.
yeah, sorry about that, everybody. Luckily, we have a backup screen sharing plan, and we are using our backup screen sharing plan right now. We want to be prepared for, hopefully, for technical snafus. We asked about the write-up for over and underfitting, and this is the place where you can get it. Looks like 4 people read it. Hopefully by next week, maybe more than 4 will have read it. And we have this slide. This is our overview of machine learning. Everybody see this? And everybody see the 12 sections? You see it? You see it, Chandrasekhar? Yeah, let me know, Chandrasekhar, if what I'm saying doesn't match with what the screen is showing, then let me know, because obviously.
Yeah, we can see that slide with different blocks and 12 blocks.
Right. So this is what we talked about last time. And so basically, what we're doing is like our goal is by the end of the class. So we have 10 weeks. This is our second week. Each lecture is about 4 hours long. Our goal is so that by the end of the class, we're going to look at this, and hopefully most of these terms, maybe not all of them, but most of them will be, certainly, hopefully you'll have heard of, and even you'll be able to say roughly what they are and be familiar with them. And some of them you'll be very familiar with. I mean, obviously some you'll be much more familiar with than others. Like today, we really want to be, this is quite critical, bias variance. And so we want to spend a lot of time on that. And so this is kind of our strategy. Let's just move on. So what we talked about last time was machine learning is really a different way of programming. The traditional way of programming is to directly program a machine. What we found was that, what society found was that having humans directly programming a machine was not a way that could yield solutions to very complex real world problems, like problems in computer vision and speech recognition. And so instead of that, we have an indirect form of programming, which basically says that rather than write a program directly, we write a program, and that program writes another program, and then that program is the thing that actually does something smart. And this program looks very different. So like, this is the kind of programming that a human would write, and this is the kind of program that this program here on the left is one that a human would write, and this is one that a machine would write. It looks very different. And in fact, the one that a machine would write really looks like a set of coefficients, set of numbers, floating point numbers perhaps even. And we talked about the sort of traditional programming versus machine learning, and this is kind of the machine learning process where we have to deal with data, and then we have to deal with algorithms, and eventually we get something. And then there's lots of iteration. And these are very costly, like iterating over different types of data preprocessing, iterating over different types of selecting and then training a model itself can take some time. The world has uncertainty in it, and we need to acknowledge uncertainty. And the best way to deal with uncertainty is to carry a representation of uncertainty along the way in all of our processing pipelines until we get to the very end, when we absolutely have to make a final crisp decision. And through a variety of reasons, both mathematical and empirical and practical, probability theory has become the dominant strategy for representing uncertainty in machine learning and artificial intelligence systems. That's not the only representation of uncertainty. We're not planning to talk about others like Dempster-Shafer theory and possibility theory and a bunch of other strategies for uncertainty in this class. But we are going to talk a lot about probability. So everybody should be familiar with probability and why, and its basic empirical sort of frequentist subjective definition. We also we gave a very simple example of machine learning, which is that you have a training set, which consists of a set of n independent and identical coin flips of some biased coin. And we count the number of times that it's heads, and we want to learn the probability that that coin is heads. And so we can write down a likelihood function. And this is quite critical, this idea that this is the likelihood of the data given the parameter. It's a single scalar, real valued parameter that lies between 0 and 1. Theta, so theta, oops, I need black for that. Theta is a number between 0 and 1, which gives the probability of heads after we've learned it. And this is essentially of saying that if the parameter was theta, this is how likely the data would be with parameter theta. But the way to actually learn, and this kind of lies at the heart of all machine learning problems, is to say, here's something that we think we want to optimize. We want to do some sort of mathematical optimization on it, and here's our optimization strategy. And this optimization strategy makes a lot of sense probabilistically. It says, okay, well, here's my data set, and I want to find the parameter that maximizes the probability of the data, since after all, the data is the thing that I observed, right? Data is what I saw. I want my model to explain this data well. And to explain the data well, it should give the data high probability, as high a probability as possible. And that's what's called the maximum likelihood estimation here. And how do we find the MLE is maximum likelihood estimation. How do we find the MLE? We do calculus, take the derivative, set it equal to 0, and after a little bit of algebra, we get the estimate, which is just the relative frequency, which is very satisfying, I think. And then we can do the same thing. This is also a review for Gaussians, where we have a sample of data. In this particular case, the data consists of x pairs. Sorry, this is not pairs yet. This sample consists. Sorry, I'm about to sneeze. The data set consists just of samples, of n samples of which in this case are multivariate or vector valued real numbers or real valued vectors, and we construct the likelihood of the data given parameters of a presumed Gaussian, which consists of a mean and a covariance matrix, which is also the likelihood. And then we can maximize either the likelihood or we can maximize the log likelihood. Typically, we will maximize the log likelihood. That was a question last time. The reason is because it's much more mathematically tractable and easy to deal with, and it gives you the same answer. And anytime there's an option between making something hard and easy, and you get the same answer otherwise, you want to choose the easy option. And so the solution is very, very intuitive also. The mean parameter is just the mean. So every time you're computing a mean, you are doing machine learning, as I said last time. And every time you're computing a variance or a covariance, you are doing machine learning. Basically, you're assuming that the data is Gaussian and you're estimating the parameters of the Gaussian of your data. So you've already done machine learning, probably many times, probably in 6th grade when you first computed your first mean, you did machine learning. Maybe it's not quite as advanced as GPT-2, but it is, something, right? You estimated a mean. We also talked about associative memories, and associative memory is a less widely used term today, but it was considered pretty important in the early days of machine learning. And I think it's important because essentially it's oftentimes what we want to do with a machine learning system, which is essentially associate an input to an output. And we have a training data set, which consists here of pairs, of input-output pairs, where X, it's by convention, X is typically the input and Y is typically the output. But what we want to do is learn to associate X to Y even outside of the data set. So like, for example, we want to choose some X that's not part of, these are the X, this is the collection of X's in the data set. We want to choose some X that's not part of this data set and have it give us a reasonable, if not a correct Y, right? And that's essentially the machine learning problem. That's the idea of taking what you've learned and generalizing it to new things that you've never seen. Imagine if you were a self-driving car and the only roads you could ever drive down were the roads you've only driven down during training, and only at that time of day, and only at that time of year, and only at that with lighting condition, and only with that particular set of cars that happen to have been parked on the side of the road when that self-driving car drove down the road during the training session. It wouldn't be a very useful self-driving car. We want the self-driving car to be able to, based on maybe a couple 100,000 or maybe 1 million hours of training data, which is actually a lot, but I mean, maybe after 1 million hours of driving a car around roads, maybe it should be able to drive along any other road anywhere else on the planet. Very much like what a human, or at least what most humans can do, right? They can drive anywhere. Once they've learned how to drive, they don't need to have driven on every single road in order to drive on every single road. So that's the idea of an associative memory. It's not like a hash table, which only can map inputs to the outputs that it was given during the training time. Right, so we're going to talk about a lot of different ways. And in fact, the strategy we're talking about for associative memory is statistical parameter estimation, where we have a training data set which consists of input-output pairs. And these are drawn presumably from a probability distribution. So there is some, this is the probabilistic assumption. That's why it's called statistical parameter estimation. We're assuming that there's some underlying probability distribution which our training data is drawn from. X, in this case, this is a regression problem. X is a multivariate vector of dimension m, and y is a real valued scalar. And we're just trying to predict the scalar from the vector. And we want to minimize the error. And so we can actually define the error. We can say, okay, well, let's say that I've learned this model, and I can take the expected value over the true distribution of the error, which is essentially how well did this learned model do at predicting y, taking the expected value over all of these things. And here's the definition of the expected value, and here's an equivalent and version of the error. And again, it's not so hard, just a little bit of algebra to find the optimal predictor by taking the derivative, setting the derivative equal to 0, and solving. We get that the best predictor is the expected value of y given x. This, by the way, should be a capital Y here. Expected value of y given x, right? And that's the best associator or best predictor of y. And that kind of makes a lot of sense, right? Which is that knowing nothing else, if we have to predict one thing for y, let's predict the mean. Like if you have a big sample, maybe the best predictor in the sense that it minimizes this error function is the mean. Now there could be other ways of measuring the error. This is only one way of measuring the error, but this is if we want the overall mean squared error to be minimized, then we predict the mean or predict the average. In this case, it's the conditional average, because conditioned on x, as x changes, we'll get a different value of the expected value of y given x. Okay. And by the way, if you're not sure about that notation, this is the definition here. So this is the definition of E of y given x here. So then how do we learn it? So we take this data set here. How do we actually do this learning? Let's actually do it when the model family is a linear model, right? So it's linear regression. This is what this means is that we're assuming that the output y is some linear function of x, right? And so in other words, the model is linear in the parameters theta. And what essentially that means, if you're not sure, is that when you have like h of, say, alpha 1 theta 1 plus alpha 2 theta 2 of x, and then that's just equal to alpha 1 times h theta 1 of x plus alpha 2 times h theta 2 of x. So that's what we mean by it being linear, which is this is linear. So linear in the parameters, and the parameters are theta. So under that assumption, we can then compute the error. This is what's called an objective function. We can compute the error over the training data. So here's our training data up here again. We have n samples. We sum up over all of the n samples, and we see, okay, well, how well does h under the current parameters theta do on the ith sample, and subtract. So we subtract how well the model does from the ith sample, take the square, and sum them up, and then divide by the number of samples, and then that gives our error, and then we can compute the gradient of that with respect to theta, set it equal to 0, and hopefully find a solution. And what we did last time is we did a matrix version of that. We said, okay, well, let's put all of our training samples into a matrix form, where the rows of the design matrix correspond to our inputs, and the rows of the y vector correspond to the outputs. And in this case, each row is just a scalar, right? So it's just a column vector, because each row is length 1. And then we can write our objective function in this matrix form, right? So in other words, this equation here is just a matrix version of this equation here. So 2.3 and 2.5, equations 2.3 and 2.5 are the same. Okay. And then we can visualize what's going on, which is that we get the famous normal equations, which basically says that our prediction, what we're predicting, no matter what we're doing, our prediction is going to be in the column space, which is this yellow stuff here, the column space of the design matrix X. And the best prediction is the one that minimizes the difference between some point along this plane, or in this case, it's a hyperplane in high dimensions, and the y vector. And the point that minimizes it is the point where this vector is orthogonal to this vector. That minimizes, because if we had instead, say, chose this guy, then that distance here, this distance would be greater than this distance, and so that wouldn't minimize the error. The one that minimizes the error is the orthogonal. It's basically like, the best way, if you're trying to get from point A to point B, the shortest path is a straight line. You don't want to go anywhere else. And so if you're trying, the straight line to any point, well, I guess they're all straight lines, but if you're trying to minimize it, the best point is the orthogonal point here. It's the one that's orthogonal. It's pointing directly out. And we also have in this particular case, a very nice matrix solution where, and this is something that we're going to be seeing a little bit later. So try to remember this thing. This is the solution. It's the Moore-Penrose pseudo-inverse of the matrix X. It's X transpose X inverse times X transpose times Y vector. That gives us the solution of the normal equations. So in this particular case, in the linear regression case, we can find the exact solution doing matrix multiply and matrix inversion. Okay, actually, before we go on in the review, let me just pause and do one of these compulsory questions. Because next we're going to talk about gradient descent a little bit as part of the review. Does anyone have any questions? Or actually, not does anyone have any questions. I will not proceed until somebody asks a question. So you're on the spot. It also gives me a chance to get a sip of water. That's the real reason why I do these pauses. So somebody needs to ask a question. It's like when we're doing, maybe this thing doesn't work on Zoom because half of you haven't turned on your video, which is unfortunate. But somebody must ask a question.
It's kind of a lower level question, but I was curious. There's a lot of alternation between referring to variables in uppercase and lowercase. And I was just curious what that tends to mean, especially in that previous slide when going over the prediction things, and then in this slide with the different kind of vector matrices stuffs.
That's a great question. So basically, roughly speaking, we're using uppercase variables to represent random variables and lowercase to represent possible values. So we might say that, X, and this is when I write X in uppercase and lowercase X, I have to be very careful because when I write quickly, they look similar. So X is a random variable. So therefore, you can talk about the probability distribution that X is equal to X, right? And so usually we can say that X is in some alphabet, and usually we'll write like script X to be the alphabet. And we can talk about the probability that X is equal to X for lowercase x in the same alphabet. So here's an example. It's like maybe the alphabet is equal to the integers from 0 to 5. So it's like a 6-sided dice, right? And so we can say that the probability that x is equal to lowercase x is equal to 1/6 if x is equal to, x is in the alphabet 0, 1, 2, 3, 4, 5, and is 0 otherwise. Right, so the x is the random variable, x is the possible value, and then this is the distribution. Okay, now in other cases, like up here, we're sort of saying that X here is this matrix. So we're gonna not like we're gonna sometimes use slightly different notation, because here X as a matrix consists of rows, and each X here is one of these samples. It's a vector valued sample from a probability distribution. So like these X's, X with a superscript I and Y superscript I, are samples from this distribution. X is still a sample from some probability distribution. Here's the actual distribution. But what this really means is that, I mean, if we were to plot this here, say, the probability that X is equal to this particular value, the ith I, and Y is equal to the ith Y, is equal to this distribution of X I and Y of I. All right, and so it's just basically saying we're drawing samples, kind of like when you flip a coin. Like every time you flip a coin, you're sampling from that coin. And if it's a biased coin, the probability of heads is, whatever it is. And if it's a fair coin, the probability of heads is 0.5. So when you could flip a fair coin 1,000 times, you could sample from a Gaussian 1,000 times. Or anytime you have a probability distribution, you can sample from that some number of times. And here the assumption is that there is some distribution. We don't precisely know what it is, but the assumption is there is some distribution, and we're trying to learn a function that maps from input to output. Okay, so that's kind of defines this. And in this particular case, we're using. I'm sorry, question?
Yeah, so just still a little bit confused about the distribution. So is that distribution directly calculated or came from our existing data set, or is it's just like an infinite, come from the infinite possibility of those X Y mapping or something like that?
Right. So this is an assumption that often you make when you're training a machine learning system, that there is some probability distribution that governs the data that you're seeing. And it's not such a crazy assumption. Like, for example, we talked a little bit last time about images, right? Like, even if you take like a 1 megapixel image, there are the kind of images that we see, day to day, like, for example, a picture of this dust-off can, or a picture of, day-to-day objects are much more probable than the kind of pictures you would see if it was truly the case that you saw random dots, right? And the number of possible images that could actually be represented in a megapixel image far exceeds the number of images that all humans have seen throughout the course of human history, even if they saw an image every millisecond. So the main point is that some images are very, very probable and some images are very improbable. And from the perspective of the distribution of real world images that you're likely to see. And so we generally assume that it makes sense to have some probability distribution that governs the data. Now, what we're not asking necessarily to know that distribution, but what we are doing is making a mathematical assumption that there is such a distribution that governs the training data and the test data and the evaluation data, the data that we're learning. And the reason why we do that is because it gives us the tools of probability to work with things like the representations of uncertainty that I mentioned earlier. And it may be like, you might argue that, well, why should we even bother to use probability? And I would say, okay, well, what other representation should we use for uncertainty? And you might say, well, let's use Dempster-Shafer theory. But I mean, in practice, it just hasn't worked as well and hasn't caught on, and it's not as elegant, and it doesn't have as nice a formalism, and it doesn't have all of the properties, at least so far. Maybe in a couple hundred years, something else will become more popular. But right now, probability theory is the way that we represent uncertainty. And so what we do is treat most statistical learning and machine learning in a probabilistic fashion. And so therefore making this assumption will make a lot of sense. Now, it might be the case, I mean, this is one of these things that, even given what I just said, you might not still feel warm and comfy inside that you know exactly the answer to this question. But this is exactly one of the questions that this class is meant to answer, because as you go through this course, we're going to see how we can use probability. You're going to actually use it in your problem sets and use it in your homework. And you're going to see how useful and elegant and how it is, and that it works, and that the techniques that we use make a lot of sense intuitively. So I believe that you will eventually get to the point where you like probability and say, yeah, wow, that's really useful stuff for a variety of reasons, both because it works practically and it has nice mathematical formalisms, and that's generally why. But what is it really, really true? I mean, is nature really governed by a random probability distribution? I mean, that's a philosophical question that, if you really think about it and you think, okay, everything is governed by string theory or whatever, if you say everything is governed by God, however you choose to truly justify the nature of reality, when we're trying to build a machine learning system, we can't get down into that level of detail. And so we have to make certain assumptions, our starting point, which is how is nature governed? And our starting point for building machine learning is that things are governed based on samples from some probability distribution. And so that's I think that's the best answer I can give right now on that question. But I think we will continue to answer it as the course goes forward. But those are both very good questions. And so thank you for answering them. Thank you for asking them. All right, so gradient descent. So gradient descent was one strategy for learning. So like in the case of this strategy, like we can come up with an objective here. We compute the gradient with respect to theta, which is right here, and then we just nudge theta in the direction, in the negative direction of the gradient. If we're trying to minimize the objective, if the objective represents some notion of cost, like for example, this is an error, and error is a measure of cost, we want to decrease the cost. We want to decrease the error. If the objective we're interested in is a measure of value, like for example, accuracy, we would want to increase the value or increase the accuracy. So whether we do gradient descent or gradient ascent, it's really only a matter of a sign change, whether we want to minimize or maximize. In this particular case, we're minimizing, and so we usually consider it as gradient descent, where we have the gradients, and here's actually the gradients of that same objective, the linear objective, and we iterate over t times with a fixed learning rate by adjusting the parameters based on alpha times the gradient, which sort of minimizes eventually the thing. And this is an example of a plot where this is theta. So this would be theta 1 and theta 2. If these are the parameters, this is a 2-dimensional vector. And this is showing contour plots of the error, showing that if we do gradient descent, it eventually, no matter where we start, it ends up at the minimum. And then we also talked about stochastic gradient descent, whereas rather unlike batch gradient descent, where we're computing the gradient over all samples simultaneously, we just take the gradient with respect to an objective consisting of just one sample. And so we take little mini baby steps. And stochastic gradient descent lies at the root of all of the success that you've recently heard about in the press of how to deep models and AI systems and all of these things you hear about. Basically, the way that all of them are trained pretty much is some variant of stochastic gradient descent, or SGD. So you should be very familiar with this. And it's very mathematically simple. It's nothing more than what you've learned in calculus, maybe with some additional ways of adjusting alpha as you go along, and maybe some additional terms. Usually what we want is alpha to decay in some way as we keep training, because otherwise, like here, this is a stochastic version. You're not always going in the perfect direction, but by and large, on average, you're moving down to the center. And as you move to the center, you want to maybe slow down a bit. And then there are more sophisticated ways that we can use that have alpha change depending on how things are looking at the time. Like for example, if we're making really great progress, maybe we want to do something different with alpha than if we're slowed down. Like if we're making very slow progress, maybe we want to increase alpha to try to boost the progress that we're making. Because alpha is kind of like the progress. It's called the learning rate. Maybe I should write that down. Okay. Last but not least for the review, we talked about overfitting and underfitting. And the idea here is that we have samples, which are these little x's. I'll zoom in on that. And we have different ways we could fit a curve to these x's. We could have a linear model, which you can see incurs these various different errors, right? These are the errors for fitting a linear model. We could have a very complicated nonlinear model, which has no error when we fit it. And we have something in between, which is maybe like a quadratic, which has some error. It's not as much as the linear model, but not as little as this more complex model. And in fact, you know, on the left, we have a linear model. On the middle, we have a quadratic model. And on the right, we have a fifth order model. So we say that the left is underfitting and the right is overfitting. And the middle is kind of just right. So what we're gonna do, this is, I think, the first, right, this is the first new slide. So we're gonna talk a little bit more about linear regression and logistic regression. And then after that, we're going to spend the rest of the time talking about underfitting and overfitting and the bias variance trade-off. And that's the plan for the rest of today's lecture. Okay, the reason why is because we want to introduce one more modeling technique, because oftentimes it's the case that the output of our model isn't necessarily a real number. Like, for example, in the case of linear regression, we fit this kind of model. We have h of theta of x, and we take a linear combination of x where theta is the parameters, and we produce an output y. But what if it was the case, oh, by the way, yeah, so here's this, I already had written this, actually, I forgot. But this is why it's linear. So the model is linear in the parameters, and in this form, this is how it's linear in the parameters. And this is fine if it's the case that our true data is a real number, right? Like if it's the case that we look at p of x comma y, and we sample from x, y, and we look at the values of y, and y is a real number, then linear regression might be perfectly fine. It might not be perfectly fine, but it at least the domain value, you know, like the range of values of y seem okay. But what if y was an integer, or what if y was just a binary number, which was you know, we just wanted to predict a binary category. Like, for example, there are lots of problems that are inherently binary. Like, for example, we're trying to make a decision as to whether or not we should buy or sell a stock. And so that's a buy-sell decision. Or we're trying to make a decision whether or not we should replace the milk in the fridge. So is the milk still good, or should we toss it out because we waited too long after the expiration date to drink it? And we don't know, but it's a binary decision. Or we wanted to make a decision about some bread that we bought at the bakery. I don't know why I'm thinking about food, but maybe it's around dinner time. But basically, we want to make a fresh, stale decision about something, about, you know, some food, or maybe we want to decide the gender of a person, or maybe that's not a good example, but there are other things. Like, for example, we have an image, right? And maybe it's the image of a house, right? And we want to decide the difference between foreground, like each pixel is either the foreground, it's one of the house pixels, or it's the background. And so each pixel needs to undergo a binary decision. There's a foreground and a background, because we want to do some sort of image segmentation, which is, you know, something that happens in Photoshop all the time. So those are binary decisions. And so if it's the case that the model is linear, you know, we could use it, but maybe it's not ideal, because, you know, do we really care about the difference between the value 10 and the value 12, or the value 12 and the value 26? Maybe not. Maybe it shouldn't be the case that we should allow the model to have flexibility that we don't really care about. So so one solution, and this actually also is a stepping stone towards the way that deep neural networks work, is to use a strategy called logistic regression. And for binary classification. Now, there are other strategies we would do for like if the label is an integer, like if it's more than 2 states, which is a binary, then there's something else called so softmax regression, which we will talk about next week. But here, let's talk about the binary case. And so the solution in logistic regression is to wrap the linear function in a logistic function. And so what it looks like is this. So basically we're saying, okay, well, rather than actually try to predict one, the actual value, we're saying, okay, well, we're going to model the probability that the output is equal to 1 is modeled by h theta. This is the new hypothesis, which is g of theta transpose times x, and g is a logistic is a logistic function, and we'll talk about logistic in a second. So in this case, theta transpose x is still the bias plus a dot product. So this thing here is the dot product. This is the bias, where we set one of the features to be 1. So we can always have a bias or a shift in the model, and the rest is handled by what's known as the logistic function. And so g of z is the logistic function, where the z is the x-axis and g of z is the y-axis, and you can see it looks kind of like this, right? It's S-shaped. At the point 0, the value is equal to 0.5, and as the value moves away from 0, it asymptotes to 1, and as the value moves away from 0 in the opposite direction, it asymptotes to 0. And this, by the way, is the logistic function is one of many functions that are known as the sigmoid function. And the sigmoid consists of things that include the logistic, and this is logistic, but also hyperbolic tangent, the arctan, and the error function, and there are a few others. And there's a nice wiki page on various different sigmoid functions that you can go to. But today what we're going to be doing is talking exclusively about the logistic function, which is one of the sigmoid functions. And there's a lot of flexibility with the sigmoid function, with the logistic function, because we can actually scale it if we want. Like, for example, here's the logistic function with various different beta scales. So if we set beta is equal to 10, which is this bottom curve, it's a very sharp transition, which suddenly goes from 0 to 1. And if you set beta to be at 0.5, then it's a very smooth transition, relatively smooth. And you can imagine that you can make this as smooth or as sharp as you want. And in fact, if you set beta to be, as beta goes to infinity, it turns into a step function or a discontinuity. So we can make it as sharp or as soft as we want, parameterized by, say, something like a beta value. Okay, one other nice thing that's about logistic is that gradients are really easy to compute. Now, this is sort of classic old neural network stuff, but the gradient of a logistic function, which is the gradient with respect to z of this, which is the logistic function, is very simple, because we would just take -1 times 1 over e 1 over 1 plus e to the negative z squared times the gradient of this part here, which is just e to the negative z. And we can write this in this way, where we take one of these. This is 2 factors. We take this out. This negative sign and this negative sign cancel out to get e to the negative z in the numerator. We take one of these factors out and put it down there. And then we realize, oh, look, this thing here is just 1 minus 1 over e to the 1. It's 1 minus 1 over 1 plus e to the negative z. And this quantity, we say, oh, look, this is just g of z here, and here's g of z. So the gradient of g is just equal to g of z times 1 minus g of z. So what this means is that if you happen to have computed g of z, which sometimes can be quite computationally costly, this is particularly important for neural networks, but if you happen to have computed g of z, and then you need to compute gradients going back for something to train, because after all, we're going to be using gradient descent or stochastic gradient descent or some form, we're going to be computing derivatives. If you happen to have g of z, then computing the gradient, you could store that value, g of z, in just a scalar register, and then get the gradient by just using it and 1 minus that value, and we got the gradient. So the gradient comes almost for free. Essentially, 1 floating point addition and 1 floating point multiply gives you the gradient, and you don't need to recompute it again. You can just store it. And from this, we can actually just define various different gradient descent rules. In fact, the famous backpropagation algorithm for neural networks was derived with a logistic function initially. And so we can, what we're going to do here, however, since we're only talking about logistic regression, we're not talking about a neural network, is that we're going to derive a gradient descent learning rule, which is similar to the gradient descent that we already saw for the linear least squares model, but we're going to drive it for logistic regression. And we're going to find that we're going to get something very interesting and similar to linear regression. Okay, so is there any questions on where we're at? So basically what we're doing is we have a different model now. So H is now something that looks like this in equation 2.1. And what we want to do is somehow learn how to train something like this. We want to find the values of theta that make the data look good. That is how we're doing learning. That is what we're learning. That is our strategy for learning. So we start with a training data set, because in order to make the data set look good, we need to have a data set. In this particular case, the data set consists of pairs, like before, except that now Y is a binary label. It's a 0, 1 valued binary number. And notice this is a set. It's not a range. It's not the real number between 0 and 1. It's just the value of 0 or 1. It's truly a binary number. And the goal is we want to formulate a likelihood function, which is basically an objective that basically gives us something like the probability of the data under a particular set of parameters, which are theta, again. And we have a probability model. We're going to do this probabilistically. So the probability that Y is equal to 1 given X under the parameters theta is the logistic function of a linear transformation of X. And then correspondingly, the probability that Y is equal to 0 is, of course, 1 minus that. So the overall function for any given Y and X pair, we can write it as H of X raised to the Y power times 1 minus H of X to the 1 minus Y power. Now, why does that make sense? Well, if Y is equal to 1, then let's write this here. That's equal to H of theta of X if Y is equal to 1, and is equal to 1 minus H theta of X if Y is equal to 0, right? And because the reason why is because when Y is equal to 0, this part becomes 1. And if Y is equal to 1, this part becomes 1. So it allows us to sort of mathematically, using exponentiation, represent the probability using one mathematical expression. And with that nice mathematical expression, there's no conditioning, right? We've sort of wrapped the conditioning, which is this stuff over here, into a mathematical expression involving exponentiation. And that allows us to do something really nice, like, for example, compute the likelihood, which is the product of these guys, and then take the log likelihood, because that is something, as we argued last time, doesn't affect the results in terms of its maximization. And what the log likelihood does, when we take the log likelihood, it turns it into y of I times log of h plus 1 minus y times log of 1 minus h. And that's just coming from taking the log of this thing, or the sum of logs of these guys. And interestingly enough, if we take the negative log likelihood, which, the log likelihood is something that we want to maximize. So it's kind of like a value, right? Anything that's sort of considered a value, like a likelihood we want to maximize, if we negate it, it becomes more like a cost that we want to minimize. And if we take the negative log likelihood in this case, it turns out that this problem becomes convex in theta. Now, convexity is something we'll talk about, and convexity is a big part of machine learning, but basically whenever a problem is convex, we're very happy, because it means that we can find the optimal solution, the very best possible theta. And so what this means is that by looking at the negative log likelihood being convex, it means that the problem has a lot of hope for gradient-like methods. So how do we get that, actually? So let's actually formulate the machine learning training process. So we can take the gradient of the log likelihood on one training pair. So we take one training sample, we take the gradient of the log likelihood with respect to theta, and what we get, interestingly enough, is y minus h theta of x times x. Now, I'm not going to go through the algebra to do this. It's just a little bit of algebra, but I can say that the derivation of this derivative uses this property, uses the property of the gradient of the sigmoid function. And because of the property of the gradient, it basically means that this gradient here becomes something that's relatively simple. It's something that we have. It's something which looks like an error, which is, this is what we're supposed to predict. this is what we are predicting. We subtract what we're supposed to predict from what we are predicting, which is kind of like an error, and it's a signed error, right? It's positive or negative, and then we multiply that times x, and x is the vector, right? The input vector. So that basically then gives us gradient descent steps, where we take, you know, the new theta is equal to the old theta plus some learning rate times the gradient, right? And then that basically gives us a learning procedure, right? It's basically alpha times the error, which is exactly this. And we repeat that process for all the different i's, and that essentially, if we do it randomly, that gives us stochastic gradient descent. And what's interesting about this is that the error has the same form as the linear case. If you remember from the linear regression case, the linear case had the answer, y, which in that case was a real valued number, minus what was predicted. So it's the answer minus what's being predicted times x. And we just keep taking gradient steps. So linear regression and logistic regression are very similar in this way. Of course, they're slightly different, right? Because in the logistic regression, y is a binary number, and h is a number between 0 and 1 because it's post the logistic function. But the form of it, which is this error times x, is the same, even though the predictions are quite different. And here's an example, by the way. Here's an actual real. This is actually from scikit-learn, of training a linear regression model versus a logistic regression model for binary data. So the data set consists of zeros or ones for different values of x. In this particular case, x, the input is one dimensional. So m is equal to 1. And you can see that there are a couple of things that are happening. So that, you know, when x is very negative, all of the y's are going to be 0. And when x is very positive, all of the y's are going to be 1. And in the middle, you can see it starts moving over to ones. But there's this period where it's not like there's one point at which you suddenly switch over to 1. It basically, like if you're to plot like a vertical line, like this is the first point at which, whoops, not that point, but this is the first point at which you see a 1. That's a perfectly vertical line. And you can see that here you've got a 1, but even if you move x farther over to the right, you've still got some zeros before you have the very last point, before the very last, hopefully this will work here. Drawing these lines perfectly lined up is hard. Okay, so there's the last point. So this line here is the last 0, and this point here is the first 1. And so there's this region here where you see both. And we're going to talk a little bit about this in a few slides, about, you know, how separable, how easy is it to get a point that separates the data in a way that gives the training data 0 error. But in this particular case, you can see that there's a threshold here. So like the linear model, if we were to train a linear model, and if, you know, the question is, well, how do we decide when it's a 0 or when it's a 1? In the linear model, we could say, oh, look, here's the prediction of the linear model. We could say whenever it's positive, we predict a 1. Whenever it's negative, we predict a 0. And so the linear model would put a threshold there, and it would say anything to the right of this threshold, we want to predict a 1, and anything to the left of that threshold, we predict a 0. But you can see that that's making a lot of errors, right? Because basically all of these got 1s here would be in error, right? And none of the 0s would be in error. What the logistic model would do is it sort of puts the threshold at a different spot, right? And, you know, eyeballing it, it probably is the case that it's doing a little bit better. Like these, if this is the, let's draw, what color should we use? Let's draw a green line for, right, so there's a line, let's move it to the right spot. So that green line, let's zoom in a little bit so you can see it better. So we have this line, which is the line of the first 1. This is the line of the last 0. And this is the logistic regression threshold line. And it, you know, just from visual inspection, it seems to be doing better than the linear regression model because the number of zeros plus the number of zeros to the right of it plus the number of ones to the left of it is probably less than the number of ones to the left of the linear regression line. And maybe that makes sense because after all, this is a binary prediction task. Now, if we were to do this in 2 dimensions, we could see that we have, data over here, which, maybe these are supposed to be the zeros, and this data over here, and these are supposed to be the ones. And we can see that this line separates the different categories of points, the 0 guys and the 1 guys. And this general property that when you have data, when you have classification data, classification means that you have like either a binary or an integer label that you're trying to predict. So y is an integer. Any such data where a line perfectly separates the different categories, in this case the zeros from the 1, that's called linearly separable data. Why is it called linearly separable? Because the data is separable with a linear function. And any linear function in 2 dimensions is a line. And any linear function in n dimensions or m dimensions is a hyperplane, is an n-1 dimensional hyperplane. So this is an example of linearly separable data. And so in logistic regression, when we take the negative log likelihood and we plot it in this way, what happens is that we end up, in this particular case, we would get a nice line that separates the data, right? And that's what this would do. But the question is, suppose we've trained this. So now we've got a point where, over here, over here it predicts something that's so remember the output of the predictor in this case is this red line, right? So basically up to the right of this threshold, it predicts a value, which is not quite 1, but it's greater than 0. And so we would predict 1. And it's not quite 1, but it's greater than 0.5. This is the 0.5 line here. So anything to the right of this is 0.5. And anything to the left of this is less than 0.5. And so if we're greater than or equal to 0.5, we might predict 1. And if we're less than or equal to 0.5, we might predict 0. So the question we want to ask is, what happens if we keep improving the likelihood? Because when you look at this kind of thing, if all of the ones, so these are supposed to be the ones, right? And so these should be ones, and this is supposed to be, these are supposed to be zeros, and this should be zeros, right? So basically, what happens if we keep trying to improve the likelihood more and more? Like what ends up happening? So is there some underlying bound that we get? And so, and let me try to give an intuition of what's actually happening here in the picture. So like this plot here, let's say that these are the zeros over here and these are the ones over here. And so what's happening is that there's a function that's kind of putting a value of 0 over here, and then it sort of slowly goes up and eventually reaches 1 over here. And it's kind of like, it's hard to draw, but it's kind of a height, if you can imagine a height off the page. And it's doing it everywhere. And so it's kind of like putting a cliff. I have a picture of a cliff somewhere, I think. So it kind of looks like, it kind of looks like this. It's like 0 along here, and in this particular case, it's a very sudden change, which suddenly goes to 1, and thereafter it's a 1. So it's a cliff between the zeros and the 1, except that there's a certain softness associated with it. Whereas rather than sort of doing a sudden jump from 0 to 1, what the logistic regression will do, depending on what the parameters, it will be 0, and then it'll slowly increase, and then there'll be this point at which it's 0.5, and then it'll be greater than 0.5, and then it'll be 1. And it's that same function everywhere. The function, the value that it's 0.5 is a contour that's kind of parallel to the edge of the cliff. And that's kind of what I'm drawing when we're back here. So like this is the sea. If we were to use that same picture, this is the sea, this is the land. And this is the line that's sort of what the logistic function is doing. And so the question is, in this particular case, we could make it as sharp as we want, but there's no bound. And in fact, what would end up happening is that, the parameters would get larger and larger and larger, and it would make sharp and sharper bound, and we would potentially improve the likelihood more and more, but we wouldn't actually do any better, right? Because we're not predicting any better from the perspective of the data. So the question for you then is, does it make sense to allow the transition to happen arbitrarily suddenly? Like, is it right to have a sudden sharp jump here for this data set? Or maybe it should be another separator, because that's another separator. Like, what if we move the cliff over there? It still perfectly fits the data. The data is, all the zeros are on the zero side, all the ones are on the one side, and there's another or another one over there. There's lots of different cliffs, all of which would perfectly fit the data. Look at this one. This one would be quite different. And if we are allowed to make it arbitrarily sharp, how would we know which one is better and which one's worse? There's no way to disambiguate them from this training objective. What's the best one? And there's no way from this training objective and from this training data set to know how sharp it should be, or should it be infinitely sharp? So this actually gets into kind of early stage machine learning, which is something called the perceptron. And this is also early stage neural networks going back to the 1950s, where people were looking at the way that neurons tended to fire. And the way neurons, from people's understanding back in the 50s, tended to fire was that there were synapses that were stimulated by certain chemical stimuli that if a neuron's synapse received enough stimulation via its synapses, then the neuron itself would emit an electrochemical charge, which would correspondingly stimulate some other neuron. And you'd have this network of neurons where each neuron would have a bunch of inputs and maybe something that would transform the input, and the inputs would be maybe summed up. And if the summed up weighted inputs exceeded some threshold, then what would happen is the output of the neuron would fire and correspondingly go on to stimulate other neurons. But if it was the case that the sum of the weighted inputs of the neuron did not exceed a threshold, then the output of the neuron wouldn't fire. It just would stay zero or something. And the kind of function that folks thought about as being a reasonable model for neurons back in the 1950s was called the perceptron. And what the perceptron threshold unit looks like is basically this. It basically says, it's actually, rather than 0, 1 values, it's +1 and -1 value, but mathematically it's kind of the same thing. And what the perceptron activation function, the activation function is this threshold, or the step function, would say that if you're greater than 0, you're +1, and if you're less than 0, you're -1. So it would be something that looks like this. So it would look like that. So it's called a hard activation function, because it's very much like what would happen in a logistic function if we allow the parameters of the logistic to become infinitely large, which is generally not a good thing for computing systems. But it turns out that if we were to do this, it would lead to the same exact learning rule. Like, the way we would learn using gradient descent would be something which would update the parameters based on their old values, and then some learning rate times this error function, or the error times the input. That's the perceptron learning rule. And you can see that perceptron learning and linear regression are kind of one and the same. And now what was interesting is that, logistic regression was known in the statistics community, and the perceptron was developed in the neurobiology community in the 1950s. And these communities at the time didn't really know about each other. They didn't realize that they were doing kind of similar things. And so one piece of evidence that, maybe the brain is doing statistics is the perceptron, right? Because if it's the case that mathematical statisticians developed a model that was so similar to what our evidence of what the brain is doing, then maybe that lends credence to using probability and statistics to help develop better machine learning systems. And that has panned out, right? So over the years, the probabilistic approach to machine learning has prevailed and has led to these remarkable successes that you're seeing now. But anyway, so one other thing that we see is that the logistic regression can fit the data really well. And this is this idea of, like I said, linear separability, when things are nicely linearly separable. There's one other thing actually I should probably mention. I should define a few terms based on this figure here. So like, generally speaking, the most important points to define the boundary are not these guys far away. This is called the decision boundary, right? This is the boundary that decides between whether it's a 0 over here or a 1 over here. And the most important points to define this decision boundary is not like this point or any of these points here, nor is it these points. Because like if these points moved over here, or if they moved over here and so on and so forth, you probably wouldn't change the boundary. But what would probably, render the boundary different would be this set of points. These points that are kind of closest to the boundary. These are points there's something called a class of machine learning techniques called kernel machines, which includes support vector machines. These are called the support vectors. These guys, and why they're called support vectors won't be clear until we understand support vector machines. But the term support vector should be clear to you, that these are the points that are kind of closest to the decision boundary, that are really the ones that are most important for the decision boundary. Whereas these other points here that are kind of far away probably won't be ones that should change your decision boundary. The support vectors are kind of the critical ones. So just to keep everybody, so support vector is something that it's kind of a useful concept to know, even if it's the case that you're not actually supporting these. Now, the other thing, of course, there's another term that I want to define here, which is this range here. This is called the margin. This is the margin here. And the margin is kind of like the distance between the decision boundary and the closest support vector. So it's like this distance and this distance. And you can see that this decision boundary here is kind of equidistant. Like the margin on each, there's two margins here. There's the margin on the 1 side and the margin on the 0 side. In this case, the margin, roughly speaking, is about the same. Generally speaking, in this kind of setting, when you have so many different options of decision boundaries that fit, that all perfectly separate the zeros from the ones, the way we disambiguate that case oftentimes is by trying to get it to be the case that the margin on both sides is equal. So in other words, the decision boundary is kind of equally distant between the support vectors on one side and the support vectors on the other side. And there's a lot of mathematical and theoretical reasons, but I think even intuitive justification reasons for doing this, which is that, well, why would, this is the closest 0 down here. Would this be a good decision boundary? Right next to this point. That's not much of an insurance policy. What if there's a little bit of error? And there's always measurement error. In everything we do, there's measurement error. And if there's a little bit of error, measurement error, why would we want to risk this point being an error? Maybe that point really should be there. In which case, if we chose that green boundary, that would be a pretty poor decision. Whereas if we say, okay, well, here's the data, let's try to make it as far away from the points as possible, then it kind of makes it resistant to any error that happens amongst these support vectors. Like if there's a little bit of more variability there and there, then it just intuitively it makes more sense, because then if things wiggle a little bit, things don't change that much. And generally speaking, what we mean by wiggle a little bit is like maybe the next day we get a data set and the points are all shifted or something relative to these. Because again, there's measurement error, there's uncertainty. We don't have perfect training data. So equal margin is generally pretty good, just intuitively. Does that kind of make intuitive sense, why we would like to have roughly equal margins? Okay, so, right. Okay, so this is now a time for questions, because I always want to force a question at the end of every one of these sections here, and maybe even afterwards. So let's let's, I've been doing too much talking. It's time for everybody else to ask questions.
I have a question. Can you hear me?
I think so. Is this Jonathan?
Mm-hmm.
Okay.
Okay, so I'm having a kind of hard time trying to conceptualize where the bias or the shift fits into all this. Is it literally like a y-intercept in like a higher dimension?
You can kind of, in this particular case, yeah, I mean, to be honest, yeah, that's a great way of describing it. You can think of it as a y-intercept in a higher dimension. So it's kind of like, in the case of the linear model, like if we're just doing a linear model, like in one dimension, which is here, it's exactly a y-intercept. It's like, okay, so where, you know, because this line, I mean, using the simple formula, y is equal to mx plus b, right?
Mm-hmm.
Which is kind of the same thing as mx plus b times x0 if x0 is identically equal to 1. Like if x0 is a feature which is always equal to 1, we can treat this as like m1 m0 dot product with x and x0, right? It's just a dot product. So it's kind of like pretending like the input is one extra dimension than what it really is, except that that one extra dimension has a value that's always 1, only so that m0, sorry, yeah, I guess m0, right? So m0, which is equal to b, becomes the bias, which in the one-dimensional case really is the y-intercept, which would be, I guess it would be this value here. So this would be m0, right?
Okay, so
and then in
this
2
would be
dimensions,
pretty vital, right? In almost every
yes,
scenario.
yes,
Okay.
it's almost every scenario, but because it's mathematically treatable, like whenever we have linear regression, let's say that we're now in m dimensions, right? So x, sorry, let's say that x is a vector in Rm, and theta is a vector in Rm. So what we could do is we could say that y is equal to theta transpose times x plus some theta 0, which is the bias, right? And we can always write this down, where we kind of have this guy sticking there by himself, always standing out. But what we generally do is we assume that instead, we assume that x is in Rm plus 1, and x is really equal to, you know, x0, x1, dot, 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 x, m, and 1. All right, I guess, sorry, that would be m minus 1 here, right? So, and then theta is equal to, actually, maybe let's put it at the bottom rather than at the top. So let's put the 1 at the beginning. So we have 1. So x is, so the input is always, the first entry in this vector is always 1. And then we have x0, x1 to xm minus 1. And theta is equal to the special value x theta 0, theta 1 to theta m. And I don't know, maybe to make the indices match, we should fix this also. So let's call this guy this. So it's x1, x2 to xm, and theta is this guy. So then what we can do is say, well, fine, okay, so now y is equal to this new theta transpose times this new x. And that's the same thing, right? Because it's just that this guy is always equal to 1.
Okay,
so that allows us to sort of do, and we can do the same thing in n dimensions. And so in the case of 2 dimensions, we, you know, it's kind of helps to find where that hyperplane is.
Okay, so the reason we have the x being equal to 1 for that first index is so that we can speed it up using matrix algebra and we don't have to add anything at the end. Is that what you mean?
Yes, there's 2 main reasons, and the one you mentioned is the first one. The other is because it's just mathematically convenient, because we can mathematically treat it identically as there being one extra input feature that's always 1. And so we can kind of forget about the bias and not analyze it, not need to analyze it, not treat it separately. Because the other reason, because the equations become more complicated, because we always have to sort of special case that guy. But we can, instead of special casing him all the time, we can just stick him inside of the matrix algebra even as we're explaining it, and then just kind of forget that the bias exists. Just thereby making the equations simpler. So by equations simpler, mathematical analysis becomes simpler, and as you said, it becomes faster because we don't have to treat it separately inside of, say, computational units like CPUs or FPUs or something like that, or GPUs.
Cool. Thanks for clearing it up.
Right. Okay.
I have
Good
one more
question.
question.
Yep.
So in the slide where we are comparing linear versus logistic, so what if we just shift the linear regression model in such a way that the line where, say, for example, the 0.5 line, maybe if we just shift the linear regression to a little bit left and we can adjust the performance to be, matching it with the logistic regression, right?
Right. So what if we did that line, for example?
Yeah.
Yeah. So we could do that. I mean, but what I'm saying is that if we were to use the training method to produce a linear regression model using the same data, when the data was really binary valued, we would get a worse performing model. Now, how would we shift it? I mean, we would need to come up with some new machine learning method that does just as well. And the logistic model works better. It produces a better, because it, in some sense, like this stuff over here doesn't matter that much, right? Like this, like the fact that this, as long as we're already one, that doesn't matter that much here. But notice that, for example, the error between this point and between this point in a linear model is different. Like this is having a much bigger impact on the error of the linear model than this model is, and then this is. Whereas in the logistic model, this point and all these points here right on the line have the same contribution to the error, which is nothing, right?
Yeah.
And the only contribution to the error actually happens down here, where it really matters. The linear model, as we move away from the decision boundary, the error grows unboundedly. And so logistics says, why? Hey, you're far away from the margin, right? Here's going back to this picture here. It's kind of like saying, where did that picture go? I can't remember. Give me a second. It's one of these guys, I think. Yeah, this one. So we said, hey, these are the ones that are important. They're the ones that define things. Why should these points over here have such a big impact on the error? Since this point and this point is just as important. They're both far away. So that's intuitively why, generally speaking, you want, when your problem is binary, to use logistic regression rather than linear regression. But that's generally true for all machine learning problems. Like if your model family does not match your data, it's not a good model family for your data. Like there are many problems that linear regression, neither linear regression nor logistic regression would be good for. Like if we only had logistic regression and linear regression in machine learning, we wouldn't be achieving these successes that we're achieving. The whole reason that deep neural networks are doing so well is because they're extremely expressive. They can express a lot of different functions, and also because they're relatively easy to train, and they use easy computational kernels like matrix multiply. One of the easiest things to make fast on computational systems is something like matrix multiply. That's, when you think about, how close, like every machine has a theoretical peak performance, right? Like how many flops can it do? Or look, this is a teraflop machine. This is a 3 teraflop machine. This is a 5 teraflop machine. This is a 15 teraflop machine. Now, just because it has a theoretical peak performance of 15 teraflops doesn't mean that when you write your program, you're going to be getting 16 teraflops. That's 16 trillion floating point operations per second. That's a lot. Some codes just inherently can't achieve that efficiency, whereas other codes can achieve closer to that efficiency. And one of the things that's good about linear models and logistic regression models, and that's also shared by most neural techniques, is that they can achieve much closer to the theoretical peak performance of the machine. So it's just easy to make them fast. Whereas there are lots of other machine learning methods that it would be impossible to get that close to theoretical peak performance. And so that gives them an inherent huge advantage over other machine learning methods, because if it was the case that I personally believe that if other machine learning methods had that advantage, that other machine learning methods would be used just as widely as deep models. But that's not the way nature works, right? So nature is such that matrix multiply is fast, and modern FPUs and GPUs do matrix multiply really fast. And hey, look, here's this machine learning method that's mathematically expressive and flexible, but you can make it really fast. So in any event, that's kind of, I don't know how I got on that tangent. That's somewhat of a tangential point, but basically, I think your question is
so by model efficiency, you mean speed as well as accuracy, right? Not just accuracy.
I mean machine computational efficiency. Like,
yeah,
like if let's say you have a machine, you spent $100,000 on a machine that can do 15 teraflops peak performance. Maybe it's not quite 100,000. These days, maybe it's more like $10,000. So you spend $10,000 and your machine can do 15 teraflops. And your manager said, yeah, go ahead and buy that machine, $10,000 expense. So you code it up and you say, okay, well, what kind of performance am I getting? I'm only getting half a teraflop. Is your manager going to be happy? Are you utilizing those 15 teraflops when you're only getting half a teraflop performance? No. So like you could potentially, if you were getting peak machine efficiency, speed up your code by a factor of 30. But it's one thing you could do is better software engineering, right? The other thing, but what if it's the case that no software engineering will make it faster, because it's just inherently something that can't be sped up because it has too much other stuff. It has too much IO, or it has too many if conditions, or too many branches that are mispredicted, or just other stuff that modern hardware can't get to go fast. Then you're out of luck. You've spent your $10,000 on that machine unnecessarily, and you might as well have spent $1,000 on a half teraflop machine, saved $9,000. Your manager's not going to be happy. Whereas if you have some other machine learning technique that can take advantage of the 15 teraflops, and you're achieving that 15 teraflops, then then your manager will be happy, saying, yes, I see that $10,000 expense is justified. And so that's one of the core advantages. So linear regression and logistic regression are actually special cases of neural networks. These are neural networks that we're talking about, in fact. Okay, those are good questions. Okay, so let's move on to the next slide. So the next 3 slides are from a review from lecture 1 again. So, and they're based on underfitting and overfitting in machine learning. Right. So this is this write-up that I did last week. So we saw this curve here. This is a review not only from lecture 1, but actually review from our review. So I'm not going to go through this again. This is a slide we saw last time, and just a question of like, what is the definition of overfitting? And we can say that a hypothesis overfits the training examples if it's the case that some other hypothesis that fits the training examples less well actually performs better over the entire distribution of instances. And this is actually a definition from Tom Mitchell's book on machine learning. And here's the formal definition. But the write-up I did actually expands upon this and makes it much more explicit. And so we're going to expand upon that in the next couple of slides. And that's going to lead us into our discussion of bias and variance. So like, what is overfitting and what is overfitting? Like, we have these pictures, these pictures kind of give us a sense, but can we come up with a more formal way of defining overfitting? So the first thing to note is that, we've got a data set D, and script D is our notation for a data set. And in this particular case, this data set is n pairs n samples, each of which is a pair, an XY pair. And they're all drawn from the same probability distribution, P of XY. And we can train a model using this training data set. So let's name a particular data set. Let's call it D sub TR, which is the training data set, right? And let's just say that this is like an accuracy. This is saying how well does H do when Y is the correct answer. And so, for example, if it's a 0-1 accuracy, it could be the case that if H gets the right answer, then A is going to be 1. And if H gets the wrong answer, then A is going to be 0. Or we could do something like that. But the main point is that we sum up over all points in the training data of the accuracy. And this is something that we'll talk about a little bit next lecture. This is a regularization term. But what we're basically doing, and regularization term is something that sort of expresses a penalty for more complex models. And so what we're doing is we're maximizing the overall accuracy minus the model's complexity. So each H has a complexity, like how complex is the given H? And so what we want to find is the H in some family of models that has the highest accuracy, but at the same time doesn't have so high a complexity, because if the complexity of H is very big, then this becomes very big and you don't get a good maximum. So it's the trade-off, and lambda is a trade-off parameter between accuracy and complexity. And this is all done, so H hat is trained on the training set, DTR, okay? And so then once we've got a trained model, once H hat is trained, we can measure the accuracy on some other data set. And this is basically saying, okay, well, we've got some data set D, and so this accuracy function is a function of D and a function of the learned model that we learned in equation 2.13. And it's just basically taking the average accuracy over the data set D. And what this means is that we can train on a training data set and evaluate on what's called an evaluation data set. This is the evaluation. It's called, so this is our evaluation data set D sub EV, and this is our training data set D sub TR, training and evaluation, right? So we can formally define what overfitting is by saying the following. So any learned model, or any model, wherever you've gotten it, we can say overfits the training data if there is some other model, H prime, such that the accuracy of H prime on the training data is less than the accuracy of H prime of H hat on the training data. So in other words, H prime has worse accuracy on the training data set than H hat, but it's the case that the accuracy overall is actually worse than the accuracy. I think, yeah. So basically, I wanted to define one other thing. So we have the accuracy. Let me just define this last thing. So the accuracy of H hat is equal to the sum, it's the expected value according to P of X, Y, of the accuracy of Y in H hat of X, which we can write it in this way. We can write it as the integral with respect to P of X, Y. So it's the integral with respect to the true probability distribution of the accuracy of Y in H hat of X, dx and dy. Okay, so this is kind of like the true accuracy here. Let's just do this so we can see both of them. We have these two different motions of accuracy. We have the accuracy on a given data set D, and this is a sum. And we have the accuracy overall, which is an expected value over all of samples. You know, it's expected value with respect to the true probability distribution. And so what we're saying is overfitting is that H overfits if there's exists H hat overfits, this H hat here, this H hat overfits if there's some other H prime that does worse on the training set but better overall, right? Now, one of the things about this accuracy is we can't actually compute this thing, right? Because we can't compute this expected value. Why can't we compute the expected value? Because, you know, as we said, we don't have access to this. We don't have access to the true distribution. We only have samples from it, which is our data gathering process. And moreover, even if we did have access to this, this would be a really challenging computational task to do. You know, this could be exponentially large. I mean, doing this computation might take us a million years just to actually compute the accuracy, even if we had this. So the main point is we don't have access to this thing. So what we instead do is, as a surrogate for the accuracy, we use this data-specific accuracy on the evaluation set. We have a separate data set, which is this guy. And so a practical definition of overfitting says that H hat overfits if it's the case that there exists an H prime that does worse on the training set, but better on the evaluation set. So if there's some other hypothesis, if there's some other model that does worse on your training set, but better on the evaluation set, then H hat is overfit. And by the same token, we can define the notion of underfitting. We can say that H hat underfits, and this is a definition, it underfits this training data set if there exists some other model, H double prime, where H double prime does better on the training set and it does better overall. And of course, there's the corresponding, if we don't have access to this notion of accuracy, we can use the evaluation set based accuracy. So it's very much analogous to how, I mean, here's the two slides together. We can use this notion of accuracy down here and down here as well, the accuracy relative to an evaluation set. So how does this look like? I mean, so generally speaking, we say that as a model's complexity increases, it gets greater and greater capability to fit the idiosyncrasies of a given data set, right? So like a good example of that was this figure here, right? So we went from a very simple model, a model that's not complex, that no matter what happens, it's going to be a line. There's no way, there's no setting of theta 0 and theta 1 that will turn this model into anything other than a line, no matter what you do. This model is kind of an intermediary complexity. It's a quadratic, but still, it's not arbitrarily complex, because no matter what you do, no matter what setting of these parameters you change them to, this will never be anything more than a quadratic. You can make it more simple. You could set theta 2 to be equal to 0. And so this model can still do this, but this model here can never do this, right? And this is a fifth order model. So this is increasing complexity. It's increasing model complexity. Right, going from left to right. So getting back to this other figure, this x-axis also corresponds to increasing model complexity. As we move from left to right, we have increasing model complexity. And so what generally happens is two things, is that as the model becomes more and more complex, which is the same thing as more and more capable, or has more capacity, more capability, the training set accuracy will keep increasing, very much like how we saw in this figure here. As we became more and more complex, the training set accuracy got better and better, right? Because you can see that the errors, these are all the errors here. Here, this was the worst error on the training set. These were the intermediary error points, and this was the best error, right? So, when we just measure the accuracy, as complexity increases, the training set accuracy increases as well. But what's going to happen is that if we have a completely separate data set, which is called the evaluation set, that there's going to be a period of time that the evaluation set, as the model complexity increases, keeps getting better and better until eventually we're going to get to this green zone, right? And the green zone is going to be kind of the point at which the evaluation set accuracy is best. But then what's going to happen is that it's going to start getting worse. The evaluation set, the set that we didn't train on, but that we're just evaluating on, is going to get worse. And in fact, it could eventually get really bad. It could get to be as bad as where we started from. So even though that the training set accuracy keeps getting better, what's going to happen is that if we keep increasing the complexity of the model, the evaluation set accuracy is going to get worse. And so what overtraining is basically anywhere you're in the red zone, right? So in the red zone, it's like if you're, let's say you pick an H prime here, that's right, an H hat. So here's H hat. If we choose some H hat, which is in this region, this is the overfitting range, right? And the reason why it's the overfitting range is because there exists some H prime in the fitting range for the green zone, and you can see that H prime's accuracy is worse than H hat's accuracy, training set accuracy. So let's put H hat right here. Okay, so you can see that the training accuracy is higher than H prime's accuracy, but you can also see that H prime's evaluation set accuracy is better than H hat's evaluation accuracy, right? Because this is much higher than this, even though this is much higher than this. So that's overfitting. That's exactly the definition of overfitting here. And then underfitting is kind of the opposite. It says, well, if you're, say, H hat here, H hat happened to be living in the yellow zone, then it's underfitting because there's some other model in the green zone that has higher training set accuracy and higher evaluation set accuracy. All right, so that's underfitting, the underfitting range. So we got the yellow zone, the red zone, and then the green zone. The green zone is where we want to be, right? We want to choose a model complexity that is commensurate to our task, to our machine learning task. The other thing I want to mention, it's not nearly as likely, but even the relative values of the training set accuracy and the evaluation set accuracy don't really matter that much to determine whether or not you're overfitting and underfitting. I mean, maybe. I mean, it's kind of crazy for this to happen, and the write-up gets into this, but maybe the training set accuracy is worse than the evaluation set accuracy. But this is still going to be the overfitting, where basically the evaluation accuracy has gotten worse, and this is still the underfitting, where there's still room for the evaluation accuracy to increase. So that gives you the same thing. Okay, so that is, I think, the formal definition of overfitting and underfitting, as well as examples of it in terms of these plots. And I think, to be honest, I mean, I don't mean to lack humility, but after scouring the web for definitions of overfitting and underfitting, I think the pictures and the definitions and the write-up that you have is the best description of overfitting and underfitting I found anywhere in all of the machine learning community. So you were here, you heard it first. So, but it's based on Tom Mitchell's book, and and I think Tom Mitchell's book is up to this point was the best. So, are there any questions at this point about overfitting and underfitting?
I had a question.
Yep.
Could you just cap in some way the complexity, and then you wouldn't have to worry about overfitting at all? You could pretty much just train as much as you wanted, or I guess it'd be like asymptotic, but then you wouldn't have to worry about it.
Yeah, that's exactly what this is doing. We're going to talk about regularization. So what if it was the case that you set omega h is equal to infinity if the complexity h is greater than some threshold and is zero otherwise. So that, there's a lot of power in this particular thing. This is like a barrier function. It says, I'm going to cap, basically give you infinite penalty if your complexity is too high. And so this argmax is, anytime h has got a complexity greater than this value tau, this guy is going to give a value infinity. And so no matter how good the accuracy is, this one's going to take over, and the argmax is never going to select it. So this is called a regularizer, by the way, and we will talk about it a lot. And this is a form of barrier regularization. It's not an easy one to deal with, but it's certainly mathematically exactly what you just described. But that is a great question. Now, another way of doing it is just to, there's I mean, that's a beautiful question, actually, because there are a lot of ways of doing regularization. I mean, one way is to explicitly do it here, right? Another way is to restrict the model family, because if we forcibly only allow the model to be a linear model, then the complexity can't ever, like, if you know, like we said that a linear model can't do a quadratic, and a quadratic can't do a fifth order. If we force it to only be linear, then that is also a kind of like a cap, right? It's kind of like saying anything outside of a linear model is got an infinite penalty. And so therefore, because we're never going to consider it. You know, another way of keeping this is maybe the algorithm itself can, you know, the training process, maybe, like, for example, we're doing gradient descent or stochastic gradient descent. Maybe we can do something to gradient descent, or maybe even gradient descent itself has, I mean, you could think of it as a beneficial limitation that because of its limitation, it can't get out of its box of limited complexity. And that is actually a very powerful way of doing exactly what you just said, which is putting a cap. Like the algorithm itself, the machine learning algorithm, even if it's the case that with another machine learning algorithm with the same age might choose it over the complex model. You know, like one of the questions that people ask a lot these days is, why do some neural networks appear not to overfit? And one of the possible reasons is because the algorithm that trains the deep model is limited, meaning it can't make the resulting learned model too complex because of its limitations. So that is another strategy, and people are thinking about that a lot. But we'll talk about this a little bit more when we talk about regularization, which will actually be next Tuesday. But that's a great question. Okay, so any other questions on fitting?
I have a quick question about fitting.
Yep.
Is there like an intrinsic difference between like the training model and the evaluation, or sorry, the training set and the evaluation set? So like, would it change? Is there something like very different about them? Could you like swap them, and would you have the same result almost in your
Well,
your model?
I mean, when you're thinking about it in the context of our current conversation, we usually think of them as drawn from the same probability distribution. So if you look at like the write-up that we have, maybe I could even, maybe it's possible I could even share a little bit of the write-up. Let me see if this works. Give me 1 second. Because the write-up goes into a bit more detail of just give me a second. Right, can you guys see the write-up?
Yeah.
Hold on a second. Right. So in this write-up, the question was inherent difference between the training and the evaluation. So we're assuming that the evaluation set is drawn from the same distribution as the training set, which means that this is true. And so we said that the training set, here was the training set up here, and the evaluation set. The only difference really is the size. So like we have different ends. Like this one is the size of the training set. This one's the size of the evaluation set. Now, next week we're going to be talking about things like leave one out cross validation and n-fold cross validation and those sorts of things. And typically, you know, we don't have at our disposal, like once we've got a training set, we don't have the ability to go out and sample more samples. We have, usually what happens is we get a data set and it's fixed, and we have to decide how we're going to split it into training and evaluation set. And there's a lot of ways of splitting a data set into training and evaluation. And rather than just choosing only one way, the best way is to choose lots of ways and take averages. And that's the basic idea of cross-validation. It's like we shouldn't just choose one way of splitting a given data set into training and evaluation. We should do lots of ways and take averages and take mins and take maxes. And if there's one case that does really bad, and we care about the extremes, or if on average it does pretty good, if we take lots of different ways of splitting it between training and evaluation, then we're usually okay, because that kind of acts as a surrogate and improves our confidence that what we're doing is the right thing. But it's obviously not perfect, because we never get a chance really. Like, this is kind of like the gold standard. This thing here, this is the thing that we wish we could evaluate, but we never really get to do this. We have to always go through our surrogate, which is this. Does that answer your question?
It does.
Okay, other questions? I would like to wait. I want to wait for one more question before we move on. So I'm just going to sit here.
I have a question. Is there like a general rule on how you would divide a training and evaluation set? For example, evaluation set generally will be a much larger end versus a training set, or like they have to have like the same kind of distribution functions for the data.
Yeah. So first of all, we are going to talk about it in detail next Tuesday. But to answer your question right now, yes, there are general rules. Generally speaking, we make the evaluation set smaller than the training set. Like, one common rule that's used a lot is 20% of the data is the eval and 80% is the training, and then you repeatedly do that. But you could imagine there's quite a lot of different ways of doing an 80-20 split, right? So maybe you'll do 5 of them, but that's not necessarily the best. Maybe you should do 1,000 of them. 1,000 splits into 80-20. Generally speaking, the more the better. And then there's also things called leave one out, where the evaluation set is one sample, and you do that. What's nice about that is that the number of times you do the split is equal to n, and then you take an average. And there are some theoretical and mathematical reasons why that makes sense. But we will talk about a number of different strategies next week. But yes, there are some ways. Okay, I think, are there any questions? Because I think this is probably a good time to take a break. So remember, we're a 4-hour class. We're going to go until 10 tonight, and we take a break after 2 hours roughly. Other questions?
Yeah, one question here.
Yep.
Well,
go ahead.
Yeah, so can a model be trained with the actual evaluation results for better accuracy?
Yes, because imagine we didn't have an evaluation set, right? So we only had a training set. So we would use a training set and we'd say, hey, look, I keep getting better and better and better and better, and keeps getting better, and there's no bound other than maybe you're tired of training. So you get to this point here and you think, hey, I'm looking at my training set accuracy and I'm doing great. And then you go to your manager, okay, we're ready to ship the product. And maybe your product is an app on the phone to do, I don't know, like there are all these kind of Snapchat kind of putting smiles on faces and stuff. I mean, I don't know, it could be any ML app that does something, right? So you say, we're ready, we're doing great, our accuracy is so great on the training set. But then you go and ship it, and actually, because your training set is limited, you test it. When you ship it, the accuracy is terrible. And because you haven't really tested it on a large data set, or you haven't tested it on samples that aren't really necessarily representative of what was presented to you in the training set. And so your question was, is there a way of using evaluation sets to improve the accuracy? And yes, so what you would do is you would choose your model H. So you keep training it on the training set, but you choose a bunch of different models, and maybe you'd slowly increase the complexity until it's the case that the complexity on the evaluation set starts decreasing. So rather than allowing the complexity of the model, like you might say, oh, look, I can go to 6th order model or 7th order model or 10th order model or 20th order model. What you're going to find is that the evaluation set accuracy is going to start decreasing. And so you'd stop increasing the complexity of the model at the point where the evaluation set accuracy starts decreasing. And that becomes your model, even though it's the case that your training set accuracy could get better if you were to allow your model's complexity to increase unboundedly. You don't do that. And the evaluation set helps you with that, helps you with doing that. And so therefore, what you end up getting is a model that's overall more accurate. More accurate when you really need it, which is after you shift the model. You know.
Thank you. So one more question that happening to that. So what are the best possible like the complexities a training model can be filled with or equipped with to have more accuracy?
Yeah, so we're gonna talk about that. I mean, in the write-up, there's a little bit of discussion on it down here. Some of which we're going to talk about, but you know, simple ways like counting the number of free parameters, right? It's very useful if you're using a neural network, or it could be the number of nodes in a decision tree. So we're going to be talking about decision trees and gradient boosted decision trees. And another strategy that's used and that's both mathematically interesting and also very practical is just the norm of the parameters and like the magnitude of the parameters. Like, you know, generally if you allow the parameters to become unboundedly large, like you saw, for example, in the logistic regression, we talked about that sharp transition. If you're allowing the parameters to become extra large, that transition can be very sharp, and that's a very complex thing. Maybe you shouldn't allow the parameters to become unboundedly large, correspondingly making the transition to be arbitrarily sharp, because it makes no sense, right? It's too complex. But then there's still other ways that we're not really going to get a chance to answer, that there are more mathematical and theoretical ways, like the VC dimension, the Vapnik-Cherenkins dimension. There's also Rademacher complexity and various different MDLs strategies, like MDL's minimum description length, and that basically measures the complexity based on how much space it takes to describe your model. Which, you know, one way you could think of it is like, if you compress your model, how many bits does it take to compress after you've compressed your model? And complex models would be ones that don't compress very well, and simple models would be ones that do compress very well, for example. And so they're like, all of them could in theory be used for omega of h. The ones we're going to be talking about mostly in this class are these colored ones, the yellow, blue, and the pink. And we will talk about it when we talk about regularization.
Okay, thank you.
But this is all from the write-up that you guys have. Okay, I think it's time to take a break, and let's come back in 2 to 3 minutes. So I'm going to pause my video because I'm going to head up and get another glass of water. But don't go anywhere. Don't, you know, stay. I mean, don't sign off, because there's a lot more to come. Only halfway done.
Hello. Can you still hear me, Chandrasekhar? You can? Okay, so hope folks come back. I think more people are online than their video indicates. Again, you know, obviously I can't force and I won't force people to turn on their videos, but if you wouldn't mind, it would be quite nice to be able to see how many people are there as opposed to just the number of login names, because it makes it much more like a real class. And I mean, if we were in a real class, then you wouldn't be able to turn off your video unless this was a, what is that show called, Black Mirror? Has anyone seen Black Mirror? I think it's the Netflix special, sort of the pseudo ultra modern utopian vision of modern society with technology gone haywire. Maybe a good episode would be having a real class, but where people in real life would be able to behave as if they were on video conference. And so they could answer by clicking, and they could shut themselves off from the future if they wanted to. They could mute themselves and would start talking without their voice coming out. I don't know. Anyone want to propose that idea? That would be pretty cool. Anyway, okay, so let's go on. What I want to do is start out by start by talking a little bit about some real world consequences of overfitting, and you know, one that is still quite strongly in most people's living memory, which is the Fukushima nuclear power plant disaster in 2011. And what's kind of amazing about this disaster, I mean, other than how catastrophic it was oh, actually I should put in ear pods. I can hear you better. Could someone say something so I could see if it works?
Yeah.
Yeah.
Hello.
Test.
Yeah. Okay. Okay, great. It works. Can you hear me still? I guess you can because you answered the question. Anyway, so the Fukushima nuclear power plant disaster. There's a lot of evidence that it was caused by overfitting, or the disaster could have been avoided, or at least largely avoided. Not the earthquake itself, but the disaster, had overfitting not happened. So what actually happened? So when they were designing the power plant, they looked at earthquake data going back in Fukushima 400 years. And so what this plot shows is, you know, on the y-axis, the frequency, and this is log, it's a log y-axis, so it's the frequency in earthquakes. And on the x-axis, it's magnitude, right? Now magnitude is itself a log axis as well, but we write it just as a linear axis in magnitude. And so what it's saying is that very small earthquakes, this is the, I think this is the yearly frequency. I can't remember exactly, but the main point is that, you know, very small earthquakes happen quite frequently, whereas very large earthquakes happen very infrequently. But you can see that in this, on these axes, when you have magnitude versus annual frequency, when you're talking about log frequency, it seems to be linear for a while, and then there's a bend, and after the bend it becomes linear thereafter. And then there's a long bit of extrapolation because, you know, these earthquakes here happen with such small frequency, such low frequency, that we don't have data for them. But what we can do is extrapolate, and we can make an extrapolation up to, you know, 9.0 and maybe beyond, based on, you know, having this curve fit to this bend, right? So that's basically the data, and so we can get a linear model. And so when we have this, sorry, we get a nonlinear model. So a nonlinear model is one that's generally more complex than a linear model, because the nonlinear model has the ability to represent this bend. And it says, okay, I'm linear here, then I have this bend, and then this data here seems to suggest I'm linear, but at a different slope thereafter. So it predicts the rest of this. And so then if you look at what is the frequency of a 9.0 earthquake and look at that value, it's very infrequent. So basically it says that there's a magnitude 9 earthquake every 13,000 years. That's pretty infrequent, right? And so if you build a nuclear power plant, you know, chances are there's not going to be an earthquake for, you know, at least a couple of thousand years. And I can't imagine this nuclear power plant still being active a couple of thousand years from now. It's not something we're going to have to worry about. They'll decommission it, you know, at least in the couple of hundred years. This is kind of like the Y2K problem. Like people in the 1950s and 60s never imagined that their, you know, computing systems would still be used by year 2000. They thought almost for sure that their COBOL programs would no longer be active. Anyway, so that's what happened, right? Now, of course, everybody knows what happened. That model was used to design the Fukushima Daiichi nuclear power plant, and they designed it to withstand, rather than a 9.0 earthquake, which happens so infrequently, to withstand an 8.6 magnitude earthquake and a tsunami of about 6 meters, right? Based on this plot. But of course, then the disaster happened, and there was a 9.0 earthquake and a 14-meter tsunami, which devastated the nuclear power plant. And to this day, it is leaking, you know, poisonous caustic radiation into the environment around the power plant and into the sea, right? You know, it's continually leaking radiation. It's going to be a long time, probably for the rest of our lives, all of our lives, before they clean it up. It's a real disaster. And in fact, it's had huge repercussions. I mean, the entire country of Germany, as a result, has decided to decommission all of their nuclear power plants in order to try to avoid this kind of disaster from happening again. That, you know, arguably resulted from overfitting. Suppose instead we didn't overfit, and instead, suppose we used like a log linear model, a much simpler model. And what a linear model would do, it's a log linear model because it's log y-axis, but it's linear in these axes. So a linear model would just continue going down gradually, and it wouldn't change the slope. It would say, well, look at all this evidence of this slope here. I'm not overfitting, so I'm going to keep the slope going down here. And so what is the probability of a 9.0 magnitude earthquake? With a linear model, it predicts a magnitude earthquake, 9 earthquake every 300 years, which is quite different from 13,000 years, right? If it's possible that there's such a large earthquake every 300 years, then chances are it could happen in the next 20 years, in the next 50 years, in the next 100 years. But point is, it might happen soon. And with a linear model, you would have had a completely different reactor design, and you would have completely avoided, you know, it would have been more expensive. Maybe you would have chosen not to build a power plant there. Or if you insisted upon there being a power plant there with this kind of model, you would have designed it very differently. So you can see the difference between this overfitted line and an accurate prediction is 12,700 years. And it makes real world consequences to overfitting. And so the moral is that, you know, you should really be careful that overfitting and underfitting is quite important. And that's true in machine learning. If you're interested in doing machine learning for your company, or you're working somewhere, you go out and your manager says, build me this machine learning model, and then it gets deployed. If you've under or overfit, it can actually have real, I mean, obviously it won't have such catastrophic consequences, probably, hopefully, as the Fukushima power plant, but it might have real financial consequences to your company's bottom line. Hence, we're spending a lot of time talking about it. So this is that idea, actually, the Fukushima, this link actually has more discussion of it, including some of the plots above. Some of those plots actually came from reading this this nice blog post, actually, from Berkeley, which I think is pretty good. Okay, so now what we want to do is we want to treat overfitting and underfitting in a slightly more theoretical way, mathematical way. And when I say, by the way, oftentimes when machine learning people say theoretical, what they really mean is mathematical. And they mean like we want to describe things, we want to understand things using the language of mathematics. Because when we understand things using the language of mathematics, we kind of, in some sense, I like to think of it as like you get it, it's kind of like an insurance policy for practice. Because if we understand things mathematically, we can say, okay, we know at the very least, we know that if these conditions are true, this will be a consequence, right? And if we don't understand things mathematically, we won't. And we're going to analyze overfitting and underfitting mathematically and also probabilistically, using this assumption that I mentioned earlier, which is that the data sets are drawn randomly from some underlying probability distribution pxy, which is here. Okay, and that's going to turn into the idea of bias and variance. And you're going to see precisely how bias and variance, no pun intended, bias and variance fit in with overfitting and underfitting. Okay. So one thing to take a note is that the training data is a random sample. So it's like when you think about, here's the training data, DTR. But that every time we draw one training sample, that is an outcome of a random experiment, right? In some sense, it's kind of like this is analogous to little x for some random variable. Every time we sample from that random variable, we get potentially a different training set. So this training data set is a random variable. Because every time we sample it, we're drawing n times from this distribution. It's random. And then what we're doing is once we've got this training set, we're fitting a model, h sub theta. Right now we're parameterizing the model using theta. Sometimes we talk about, I hope this is not too confusing, but sometimes we talk about h in h. And other times we talk about h of theta with theta in some, parameter space theta. It's kind of the same thing, except here we're talking about the parameters of the model. Here we're talking about the model itself. There's not really any difference between this and this other than notationally. Sometimes we do this because we've got enough other notation to worry about without having to worry about theta. Other times we want to worry about theta explicitly because there's something we want to do with theta. Like, for example, talk about a dot product, right, between theta and x. But the main point here is that we're talking about h sub theta, where h is derived from the training procedure, meaning that h is something. We have a machine learning algorithm. This is this algorithm which takes the data and writes the program. And the program, which it's going back to our original picture, the program is represented by the learned model, which is some value for the vector theta. So therefore, we can think of this itself as a function, theta of d. Theta of d is a function that maps from a data set to a parameter vector. And the function, in order to run that function, we need to run the machine learning algorithm, right? We need to, and it's kind of like, think of it as any function in Python or C or whatever language you have. The argument to the function is the training data set. And then the last thing you do is you return the resulting learned parameters. However, theta of d is a random variable because d is itself random. Whenever we have a random variable and we take a function of a random variable, that function is also, the value coming out of that function is random. So theta of d, you can think of itself as a random variable. Even if it's the case that the machine learning process has no randomness in it, the input to the machine learning process, which is a random data set, makes the output of the machine learning process random. Right, so this is essentially saying the same thing. Every time we draw a different training set, which is random, we might get a different theta. Hopefully, it's the case that the thetas we get, like for example, if we have, suppose we have D1 of TR. This is our first data set, and we have theta of that, and we have theta. It's the same function, but it's on a different data set. So we have the second training data set and the first training data set. And the question is, how equal are the resulting learned models? they might be very similar to each other. They might be identical. They might be quite different. When are they different? When are they how, and if they are different, how different are they? How much do they vary from each other, between each other? How much do they vary around their mean? And what do we mean by their mean? I mean, we could compute something like, since this is a random variable, we could compute things like the expected value of theta of d tr, right? This is you know, where does the randomness of this expected value come from? It comes from the fact that this is a random data set. So every time we draw a different data set, we run the machine learning algorithm, we get the output of the machine learning algorithm, and we take the average of all of these machine learning algorithm outputs together to give us a mean. And every time we do it, how different is the output from the mean? There's also a variance. We could actually compute the variance, which is the average difference between the output and the mean squared. Right? So that, I mean, just like any random variable, we can compute a mean of it and a random variable, sorry, and the variance of it. So, but by the way, that should hopefully clue you in a little bit on the word variance. Like, why do we call variance variance? Well, it's no coincidence that we're essentially treating the output of a machine learning process as a random variable. But you'll see more precisely why we call variance variance in a second. Right. So when we're actually training, or by the way, training and fitting are synonymous. Python, like whenever you use Python, it's always, they use the word like .fit. Right. So, but that it could also be called .train. .fit comes from statistical fitting, comes from statistics. But whenever we're fitting a model or training a model to the data, we optimize some model in the model family. So like it's either a linear family or a logistic model family, or it might have some higher order features like the polynomials we talked about earlier. Whenever we're doing some training, we can either have high bias, low variance, which corresponds to underfitting, or what we'll see in a second is, which will go on the next slide. We're going to see a bunch of bullet points here. We're going to see a bullet point there, 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 and then here we're going to have low, not how bias. We're going to see low bias, high variance. I can't write today. And this is overfitting. We're going to see a bunch of bullet points there. So first we're going to go through the bullet points for high bias, low variance, and underfitting, and then we're going to go through the bullet points for low bias, high variance, which is overfitting. Okay, so let's do underfitting first. So if it's the case that the model family has low complexity, meaning it's too simple, then what that means is it never will match the properties and the characteristics and the aspects of the data that we care about. In which case we say that such a model it is biased, right? It underfits, it regularly underfits because it can't really find and represent the important properties that exist in the data. But at the same time, if we train on multiple different data sets, since the model is so incapable, you're kind of going to get the same thing. You're going to get the same model over and over again for different data sets. All of them are going to be wrong, but they're all going to be wrong in the same way. Right? So kind of like all are wrong in the same way. And if they're all wrong in the same way, that means that they're not going to differ very much from each other, which means that if you compute their variance, how much they vary from each other, they're not going to vary a lot. They're going to be all wrong in the same way, but the variance is going to be small. And so therefore it's going to have low variance. So this corresponds to underfitting. On the other hand, there's the low bias, high variance case, which, as you can imagine, hopefully is going to correspond to the case when the models are very complex. So when the model is a very complex family. Like if it's higher order polynomials, or if it's a very deep network, because by the way, depth generally increases the complexity of the model, then what's going to happen is that the bias is going to be low. The training data is going to match really well. It's going to say, yeah, I can fit that. I can fit that too. And then some other training data set comes along, and that model family says, yes, I can fit that one data set. And no matter what you throw at it, what data set you throw at it, it's going to say, yeah, I can fit it. But then the problem is that for different data sets, it's going to get very different results, because every data set's going to be different, since after all, these are random data sets. They're drawn from a random process. And so each data set is going to have some probability of being different. And generally speaking, if you have small data sets, the data sets are going to look very different from each other. The small data sets properties, or the properties of the large, are not going to show themselves very well. And so each small data set, or even any data set, it's going to have idiosyncrasies. Idiosyncrasies are sort of characteristics that are exclusive to that data set, that are not common to the whole distribution. And so when you have a very complex model, it's going to overfit. It's going to say, yeah, I can capture those idiosyncrasies of that data set. And yeah, I can capture those idiosyncrasies of that other data set. No matter what data set you throw at it, it's going to capture those idiosyncrasies. And but that means that every time we train a model, it's going to be different. And so the trained models are going to be different from each other. So the variation of these models are going to be different. So the variance is going to be high. So when you do overfitting, when you have the possibility of overfitting this high complex setting, you're going to have high variance. So we have high bias and low variance, which corresponds to underfitting, and low bias and high variance, which is going to correspond to overfitting. Now, I think that variance might even be, at this intuitive level, a little bit easier to understand than bias, because the idea of like multiple, training the same techniques, you have a machine learning algorithm which trains a model. Every time you train it on a different data set, it's going to give very different results. That sort of indicates that it's high variance. It varies a lot. Whereas if you have a machine learning method that no matter what data set you throw at it, it produces almost the same resulting model, the model is not going to vary a lot. It's going to be low variance. I think that the variance idea kind of makes sense. The question is, well, bias, what do we mean? Like, what does the word bias actually mean? And it's going to be wrong. But the question is, we want to quantify. We want to mathematically describe precisely how it's wrong and why is it called bias. And we'll do that in a few slides. Okay, so just to expand upon bias variance, our goal, of course, is this this supervised learning thing. We want to find this associative memory, whether it's either a classifier like a linear model or a regression, a classifier like a logistic model or a regression like a linear model, and we want to find the one that has minimum error. And also, let's just for a moment think about regression. Although the same exact thing happens for classification, whenever we want to minimize the error, like in this particular case, we use squared error. Right? So here's the squared error. We're basically taking the expected value with respect to the true distribution of the difference between the model's prediction and the true answer squared. And we want this to be small. And we can do this, and we take the gradient or the derivative of this with respect to h. And this is actually solvable mathematically. And we get that h star, the best possible model, is the conditional expectation. We did this last time. It's the best association. It's the best you can do. If it's squared error, and if for each x you're required to predict only one y, the best you can do is predict the conditional mean. Now, to do this practically, this basically means that we have to have the actual distribution p. Do we have p? Do we have the resources to compute this conditional expectation? And this also assumes, and this is an important one, that the model family spanned by the models that we're learning over includes the functional form of EY. In other words, this is this notion of realizability, and this is an important term in and of itself, the realizable case. this term here, realizable. And what realizable means is that the thing that you're trying to learn lives in the family of models that you're learning over. Let me write that down. The thing you are trying to learn lives in the family of models you are learning over. For example, let's say that the family of models that you're learning over are linear models. So the realizable case would mean that truth is linear. It would mean that it really is the case that y is equal to theta transpose x. You know, maybe with some noise or something. But the main point is that truth really is a linear relationship. There's truly a linear relationship between x and y. Or, and if you're learning a linear model and truth is linear, then that's realizable. It means that you have the thing you're trying to learn lives in the family of models that you're learning over. Another example would be what we've already saw, logistic regression, where we have y is equal to g of theta transpose times x, where g is the logistic function. And if truth is such that basically every y is truly computed by taking an x and taking a linear transformation and applying the logistic function, and if all you're trying to do is find theta, then that's realizable. But the main point is that, you know, none of these things are really true in practice. Like this stuff, we don't have the distribution p, we don't have the resources to compute y, and most of the time what we're learning is not realizable. Meaning even if we're learning a linear model, it's not necessarily the case that there's truly a linear relationship between the x and y's. Why would we then use a linear model? Well, for a variety of reasons. It's fast, it's simple, it's easy to interpret, it doesn't have a lot of parameters, it doesn't require a lot of memory, and we can get oftentimes it's good enough. Like it doesn't need to be perfectly accurate. You know, maybe it's better if we're not going to be perfectly accurate. It's better to be inaccurate in a very simple way than to be inaccurate in a very complex way. Like you might instead start off with a 153-layer deep neural network, and you might still be just as inaccurate, but your inaccuracy is very complex. Whereas in linear models, your inaccuracy is relatively simple. Okay, but any of the assumptions we don't have, but this is still equation 2.18 is the best we can do in theory. So in practice, what we have, rather than the probability distributions, we have this training data, D, right? And we have a limited model family. And by limited model family, we have that truth is not a member of script H, right? It's like script H, that might be all linear models, but the true model is not linear. So therefore truth is not a member of H. It's not realizable. And so what we do is we say, okay, well, we have squared error. We've got our meager training data set resources. And what we do is we find amongst the set of, say, linear models, the one that minimizes the error on the training set. So we sum up over the training set, we measure the error of every sample, we take the average, and then we choose the one that minimizes it. And we can often, we can do that by calculus. You know, we take gradients and set it equal to 0 and do gradient descent or whatever. So the question is, we want to analyze the difference between the optimal case. We want to mathematically analyze the difference between the optimal case and the practical case. And there's two main reasons why it might not be good. It could be the case that we have the wrong model family or not enough data. But by not enough data, what that really would mean is that we don't have a good representation of this probability distribution. Now, you know, it could also, of course, be that, you know, there is no true probability distribution. That is, like I said, that's a philosophical issue. We're making the assumption that there is a probability distribution. And if we have enough data, you know, by, you know, the law of large numbers and so on and so forth, any statistic that we could get from the true distribution, we can get by a large enough sample, right? But if we don't have a large enough sample, meaning our training data size is too small, things are not good. So let's see if we can think about this. So one way of measuring how good we are could be we could say let's measure on the data set that we trained on itself, right? Like this thing here is analogous to where did that picture go? I think I can actually do something that you guys might like. Just give me a second. Is this going to work? Just give me a second. I think this will work. Let's see. Maybe this won't work. Okay, I thought it was going to work. Let's just try it again. Okay, let's try it this other way. This is one of our earlier slides. That's not what I was originally hoping to do. I wanted to just get the figure, but you can see that if we just measured this is the thing. We're measuring on the training data set. This is the error on the training set, and it's kind of analogous to the accuracy on the training set. So here we're talking about accuracy. Up here we're talking about error, but you can see that they're related. They're inversely related to each other. So if the accuracy is high, the error is low, and if the error is high, the accuracy is low, right? So if the error keeps going up, if the accuracy keeps going up, then the error is going to keep going down. And the evaluation set accuracy, like we could have a similar kind of plot where the accuracy keeps going down, and the evaluation set accuracy goes down, but then the evaluation set error starts going up again. So that would be the analogy of this plot, but using error instead of accuracy. And so, evaluating how well we're doing by computing the error on the training set for reasons that we talked about in the overfitting and underfitting section is a bad idea, because you're going to get a poor, especially if you're in this regime, in the red region, you're going to get that overfitting problem. So we're going to get lots of different, each time we train, we're going to get very different Ds. We're going to get different solutions, but they all might look good. They all might look good. So like each time we train, the accuracy might get really high on different data sets, but we're going to get very, very different solutions. Like just because the accuracy is good of this model on this data set doesn't mean the accuracy is good overall. Same with the error. Now, the ideal approach would be to not use the data. I mean, we've kind of already said this, but the ideal approach would be to not use the training data to see how well we're doing, even though what we're using the training data for is to produce a mathematical objective that we're trying to minimize. And we could do something like this, but the problem we said, is that this is impractical or impossible. We just can't. We don't have access to P. This is too computationally costly. And so what we do instead is we generate another data set, an evaluation data set. And so let's use script T. Script T and D, our training set, have no intersection. And we try to get an estimate of this. This is kind of like the estimate of the accuracy using this. So by the way, I should mention that this, in the write-up that I sent out, this is kind of analogous to the accuracy of H hat. And this is kind of analogous to the accuracy of the data sets, of the evaluation data set of H hat. Right, but we're just changing the notation here, specifically talking about the squared error rather than some, just some general notion of accuracy. Right? Here we're talking about a very specific error, which is the squared error. I should mention, I mean, as we go through the course, you will learn that there are many ways of measuring error, and there's many ways of measuring accuracy. Here we were talking about general concepts. Here we're talking about a very specific way of measuring error. And we're talking about, you know, a regression problem. But the main point is that T, you know, so T here is equal to the D of EV. So those are the idea is that's the same thing. So in fact, maybe notationally we should start calling this DEV rather than introducing T. But the main point is that these guys don't intersect. Okay. Okay, so we have two things. We have the ideal solution, the ideal mathematical solution, and we have the solution that we have obtained using our machine learning procedure. And we want to compare the two. Now, before we do that, let's just measure the overall error for any H, right? So this is the notion of the error. So H is some hypothesis. And we're doing, this is now a mathematical problem. We're sort of analyzing this mathematically before we introduce this thing. So we're not going to introduce this again until we get to the next slide. So put this on the side burner for a moment. And let's talk about the overall error, where the overall error basically takes the expected value of the squared error between the current hypothesis H and Y, you know, averaging over the true data distribution. And here's just basically, here's the definition. So we've got this joint distribution. We're using the conditional probability to represent to break it into P of Y given X times P of X. It's an integral. And now what we're going to do is we're going to add something a little bit funny. We're going to add 0 to it. All right, so actually I'm going to use a different color for that, something that's more distinct. So this thing, we're going to do, this whole stuff here is equal to 0. So it's E of Y given X minus E of Y given X. So you can see that all this stuff is equal to 0. So therefore it's equal to that. But now we have H of X minus E of Y given X plus E of Y given X minus Y quantity squared. And so we can complete the square. We can say, well, that's equal to this squared, this plus this squared. And that's kind of like the same as A plus B squared, which is equal to A squared plus 2AB plus B squared. Right? Just completing the square. And so it's equal to A squared plus 2AB plus B squared. Right? But with a little bit of algebra, you can show that by taking the expected values inside, you can write that this is equal to A squared, which is the same as this, plus B squared, which is the same as this, plus this, which it's because of the linearity of expectation. And the critical thing is to note that this second term cancels out. I mean, you can right away see that this second term cancels out here, because it's E of Y given X minus E of Y given X. That's equal to 0. Now why is that? Well, it comes from this guy. And so the question is, why does the second term cancel out? And it's basically because of the properties of conditional expectation. So the properties of conditional expectation say, first of all, that, okay, well, what is the definition of E of Y given X? So X is a particular value, Y is a random variable, and E of Y given X really is defined to be equal to this thing. So it's basically the expected value of Y under the conditional distribution P of Y given X. This is by definition. And this is our best predictor or best association or best, you know, regressor, assuming that we had perfect knowledge and perfect ability to compute for a particular value X. Right, and that's what E of Y given X is. Notice that this is a function of X. It's not a function of Y, it's just a function of X. Right, so in other words, Y is a random variable that gets marginalized out. The only input to this thing is the value X. Right? And it's a deterministic function, right? We put in one value of X, we put in the value of 3, we get something else, a single value out. We put it in the value of 7 for X, and we get something else out. But what we can do is we can turn X into itself a random variable. So now X is random, and we're taking, it's kind of like a random integral, right? Because capital X is a random variable, and we're taking this random integral, and so therefore the outcome of that integral is itself random. And so this is a deterministic function of this random variable X. And so therefore this quantity here, where X and Y are both capitals, is now a random variable. And that random variable itself has a mean, right? But this mean is E according to P of X of E of Y given X, right? Because this is the random quantity, and when we're computing this mean, this is equal to this thing. The randomness comes from the fact that this is the random variable, and whenever we have a function, whenever we want to do E of X, right? But this is just equal to the integral of P of X dx, right? And whenever we have E of F of X, that's just equal to the integral of P of X f of X dx. And so this is the same thing, except that the function f of X is really just E of Y given X. Okay, so what happens then if we take the expected value of Y given X? First of all, it's well defined, right? Because we said that this is a random variable. This is the same thing up here. And it's like a double expected value. But in this first case, the inner expected value is with Y, but now we're feeding it a random variable X, and the outer expected value is taking expected value with respect to X. So we can just write it down in this way. And then this is just expanding it out. But once we have it expanded in this form, we can use the commutative property, and we can kind of shift things around. I mean, there's formal limit, mathematical analysis reasons why doing all of this is valid. But, assuming certain continuity properties are true, we can sort of switch the order of integration, and we can bring the dx inside and the dy outside. And what we end up getting is that this quantity here is equal to this quantity here. And this is just something, this here is just P of Y comma X, right? Because it's just the chain rule again. And so that whole integration of X on the inside cancels out. So what we're left with is just the expected value of Y. So what this is saying is that E of Y given X is equal to E of Y. And because of that property, then what we end up getting is that this whole error, this is this long process of getting this thing, that this whole error function here, which is the overall error, is such that this cancels out. And what we're left with is the first term and the second term. This first term and the second term. So let's now write the error in terms of just the first term and the second term with this middle term canceling out. So here's the first term and here's the second term. So let's look at these guys. What the heck are they? Right. So so this is the error. First of all, this is the error of a given hypothesis H, right? And the error consists of two terms. Let's talk about the second term. Like what we really care about, it's the error of H. The second term has nothing to do with H, right? Second term, notice that H is only involved in the first term. And this is kind of like the overall model error. Sorry, it's the overall, I misspoke. It's the overall inherent error, right? Because it's saying, think about this term inside here. It's saying, this is the best possible thing we can do if we insist upon making one prediction for Y for a given X, right? That's the best we can do. And here's the actual value of Y. And it may be the case that the actual value of Y that happened under this distribution is not equal to the very best predictor, because the very best predictor doesn't mean it's the right answer. It just means it's the best single predictor under a squared error. And the best single predictor could still be quite wrong. And it's saying, okay, well, for under this, you choose a particular XY, you weight it by its probability, you compare the difference between the best single predictor and the actual Y, square it, and you take the expected value of the whole thing. That's error we can't control. So what's nice is we've broken the error in terms of a term that we can control, which is an inherent property of the problem. That no model, no H, no matter what family we're choosing from, No model will ever be able to decrease this because it's a fundamental property of the problem that we're trying to learn. The first term, on the other hand, is very related to the model that we're trying to learn. And it's saying, okay, well, I mean, let's again look at the inside part. It's saying this is the best single predictor of y for a given x. And this is the predictor that h does. This is the prediction that h does. And it's saying, okay, well, how close is h from the best single prediction, taking the quantity square, and then weighting it by the probability of that particular pair, and then summing over all of those guys. That's the first term. The first term is sort of like, is the fundamental learning errors, like how bad a job did we do learning? And so since it's the case that we can't really control for this, let's only focus on this in deciding on how good h is, right? Because that's after all the game we're in, right? We want to say how good is h? We do know that if it was the case that h was equal to h star, which was the best predictor, then h would have zero learning error, even though it would still have non-zero inherent error, because we can never drive this to zero, unless we of course change the distribution or change the problem, which we can't do. Usually you can't do that in machine learning. You're saying your manager comes to you and says, hey, learn this. And you can't say, let's say your manager comes to you and says, I want you to do self-driving car prediction. And you say, sorry, I don't want to do self-driving car prediction. I want to do cancer, cancer prediction based on radiological exams or something. That won't work. Even despite how good the problem is, you can't change the problem you're doing. So anyway, then there's one thing we haven't yet. Remember we said earlier that this guy up here, we're going to sort of pause it for a second. The fact that what we've learned is itself a random variable. Let's bring this back in. Let's bring this random learned model back in, where the data set comes into play. And remember that this is a random learned model that's been learned from a data set. And let's look at, since this is the thing we know we can, that determines the overall error that we can kind of control by choosing our model, let's plug in for h sub d, right? Which means now that h is now a random variable because it's going to be h sub d. And so that means that, for example, we can actually compute something like the expected value with respect to d of h of d, and we can even compute its variance, right? Like these are meaningful quantities because this is now a random variable. Remember, the randomness is coming from the fact that d is a random variable. In fact, one of the things we're going to do, this might seem like it obfuscates the notation, but in fact, it's going to clarify the notation, because we're going to use two different d's, d and d bar, to be able to express things like the variance, because it's the expected value with respect to the random variable d of h of d. So this guy's using this d, but then inside we have the mean, right? So this is the mean with respect to d bar. But the key thing is that d bar is the same, it's just another copy of the same random variable. And so we can compute the expected value with respect to d bar or the expected value with respect to d. It's the same thing. But it just makes it clear that this expected value that's computing this mean is using d bar, whereas with respect to this expected value, this is now a constant, because that's now a mean that's already been computed. And we want to compute the average of how far away this is from its mean squared. Hopefully that's clear. So what we're going to do then is further analyze this first term, like I said, where we replace h with h sub d. And we're going to break that down into pieces too. And here's the derivation. So I don't know if we can see both things. Can you see both things at the same time? Yeah, if you look at the very top, look at the very top equation, no, that's not good. Let me just let's see if I can copy this. This should work. Should be able to copy equations. It worked when I tried it earlier. Why is it not working now? Okay, this is like you can see it's a bad quality copy, but this is a copy of equation 2.13 that you can just see. I just copied it over so you can see it in the same slide. But the derivation is all here. Okay. This is the equation from up above, a few slides above. But okay, let's go through this then. We've got, we're taking this first term, and we're plugging in h sub d for here, and then that's going to give us this first term. So what we're going to do in the next step is we're going to do the same trick. We're going to add 0, which doesn't change anything. In fact, in this particular case, what we're adding is a different form of 0. We're adding the expected value of our model minus the expected value of our model. And so now again, we have the expected value with respect to d of a plus b, and we can complete the square in exactly the same form. And that's equal to a squared plus 2ab plus b squared. But for very similar reasons as what we saw before, I mean, if you bring this expected value in here, you see that in this particular case, this first term becomes 0, right? Because we've got the expected value of d here and the expected value with respect to d here. And so that minus that becomes 0. And so the second term cancels out. And what we're left with is the first term and the expected value of the first term and the expected value of the third term. And what we end up getting is this guy, which is what's called the variance, and this guy, which is known as the bias squared. And this is the bias variance decomposition of the model. So now to get the overall bias and variance, note that this is for a particular x. We still, when we went back, like when we go back to equation 2.31, we're taking the expected value over x and y. We need to take the expected value over x to get back to the overall bias and variance for all x. Because this is all the bias for a particular x and the variance for a particular x, and we take that last expected value. Okay, so let's analyze that. So just to connect the previous and the current slide, we had the variance, which is the variance, and the variance, and this is the expected value with respect to x of the variance. And we have the bias squared, I'm sorry, I made a mistake there. I wanted to match the colors to the equations. All right, so you can see that this is the variance, these are all variance, and these are all biases. Except the only difference here is that in these equations down here, we're taking the expected value with respect to b. Okay, so that's now connected, so let's move up. So let's take a look at this and see what it is. Well, what should we do first, right? So let's do variance first, right? Oh, I forgot, there's also bias, right? So why is this called the variance? Well, first of all, you can see that this is the mean. This is the average over all data sets weighted by the probability of the data set of the learned model, right? So remember, this is the result of the learning process using this data. It's a random variable, but we're taking the expected value. And then this is for a particular x. And then this is actually just one particular data set. And then we're taking the difference between that and its mean and then squaring it. And then we're taking the expected value of that squared quantity with respect to this outer random data set. And then lastly, we're averaging over all x. So it's a variance, right? Because it's basically just like saying the expected value of a random variable minus its mean. and then we're doing one more expected value of the outside, and that's a variance. And what we're going to see is that as the model complexity increases, this variance term is going to increase. The bias, and now it should hopefully after this make sense why we're calling it bias. The bias is saying, okay, well, this is the best single predictor we can do, and this is the average of the predictors that our machine learning method does, right? And we're taking the square, again, weighted over all x. And so we're saying that we're very biased if it's the case that we're far away from this best predictor, right? This doesn't have anything to do with it, which is very much like, for example, you know, when we have a linear model trying to fit a polynomial, you know, no matter what data set we get, we're probably going to get the same thing. It's not really a variation thing, but it's basically always going to be different from the true polynomial. The linear model is always going to be an error. And so these are the errors that the model makes. The average error, that's right, it's the average prediction minus the true best prediction. And it's kind of like the errors that get accumulated over all x. And so similarly, we see that as the model complexity grows, the bias is going to decrease, or the bias or bias squared. I mean, it doesn't matter much. I mean, we usually just say bias, we don't say bias squared. But what the bias variance trade-off actually does is decompose it into the variance and the bias squared. And you can see that there's this trade-off, right? That the total error, or the MSE, is decomposed into the variance and the bias squared. And when you add these two things up, you get the total error, which is this quantity here. And when you add the two things up, there's this blue curve, right? So so here you have overfitting. Here you have underfitting. So overfitting, you have high variance and low bias. Underfitting, you have high bias and low variance. And here you have fitting, where you kind of have the best trade-off. Where the trade-off is determined by the sum of the bias and the bias squared and the variance, which gives you the best overall error. Okay, I think this is a good time to pause for a question, because we've derived it and we've connected it now formally to overfitting and underfitting and bias variance.
I think there's a question in the chat.
Oh, thanks. In the chat. Okay, what's the difference? The question is, what's the difference between E sub D and E sub P of X? So I'm just wondering if I should do a new slide or go on one of the old slides. Let's do a new slide. So remember, so the difference between E sub D and E sub P of X, right? So first of all, they're both expected values, right? But the expected values are very different things. So let's do case one first, right? E sub D. So remember we said that we have the machine learning process. So theta of D is equal to the process of learning model parameters. I'm sorry, my handwriting is terrible, which is why I use slides a lot. I just naturally have terrible handwriting. Model parameters based on a data set, right? Now we have that the data set is equal to, it's basically x1, xi, yi, for I is equal to 1 to n, where x of I and yi are drawn from P of xy. So each sample is a random sample, and so therefore the data set is itself a random sample, right? So we can say, for example, we can talk about things like the probability. We don't have like an uppercase and lowercase. But let's say that the probability that, I'll have to write this really slowly, that bold D, which is the random variable, is equal to a particular instance of that random variable is equal to the product for I is equal to 1 to n of the probability of x of I is equal to x, lowercase x of I, and y of I is, actually, we don't even need the i's there. So it's like, it's x is equal to xi, comma, y is equal to yi. So this is the distribution of data sets. It's using the same underlying distribution that you do as the sample, but every time we choose a data set, its probability is equal to this. This is the probability of a data set. So whenever, for example, we say something like, what is the expected value with respect to D of, say, H of D of X, right? Like we write things like, I mean, in the previous slide, we write things like that, right? So what this really means is the sum over over all data sets. We don't have a good notation of all data sets into the space, the set of all possible data sets of size n of h of the parameters of D applied to a particular sample x. Right. So basically what we're doing is we're taking the expected value with respect to the fact that the data set is itself random. Right, because it's a random quantity. Right. And in this notation up here, we're not explicitly talking about the theta. We're not talking about the machine learning process, because the notation would become too unwieldy if we stuck thetas in there all the time. So we're not actually putting the thetas in there. But what we really mean is that it's summing or integrating over all possible size n data sets for each one of those infinitely large, like how many data sets are there of size n? Obviously, there's an infinite number of these. So this is an infinite number of terms in the sum. Or if it's an integral, it's an infinitely large integral in some sense. And so for each one of those infinite number of data sets, we learn the model, we predict x. Oh, there's one thing that we're missing, actually. I forgot one thing. And then there's then we have the probability of the data set, right? Because obviously we're computing the expected value. So we want to weight this prediction based on the probability of this data set. And that probability is the same as this probability here. But here we're just explicitly mentioning the random variable. Here we're just talking about the outcome of the random variable. Okay, now E of P of X is a lot simpler. That's basically just, whenever we take E of P of X of X, that's just the expected value of X, right? So that's basically according to distribution P. So that's basically equal to the integral of x, p of x, dx, right? So we can also talk about e of p of x of some function of x, which is e of x, so e of f of x, p of x, dx. That's just the expected value with respect to just the probability distribution x. So it's the underlying source of the probability is still the same. It's this distribution, but the way that we're using it is different. Either we're taking the expected value with respect to a bunch of random data sets, or we're taking the expected value with respect just to a particular value, just particular random variable x. But they're both expected values. I hope this answers your question. Are there any other questions? By the way, I want to mention also that these slides, as well as the annotated slides and this picture I just drew and all this kind of stuff will be posted after lecture. So you'll be able to review this as well as the YouTube lecture as well, including all my mistakes. So if I make a mistake, and I make mistakes, then it will be posted on YouTube. And I hope that me making mistakes will encourage everybody to ask questions, because like I said, that's how you learn, by asking questions. Actually, our TA, Chandrasekhar, is an expert at asking questions. And I know I've known Chandrasekhar for, I don't know, how long have we known each other? Like 7 years now or something. Yeah, so that's meant as a compliment, because actually the way to learn the quickest is to ask the most questions. One of the things you notice, like if you're in a room, most of the time, not always, the person asking the most questions is often the one who learns the fastest, because they're curious and they want to learn. They're not afraid. And I think that's one of the reasons why people don't ask questions, is because they're afraid. Fear. The only thing to fear is fear itself, right? To give you a cliche. So, all right. So let's go on with this bias variance stuff. So we say that an estimator is unbiased. This is an important term to note. If it's the case that the bias is 0, and how would the bias be 0? If it's the case that our estimator has expected value equal to the best predictor, right? So let me copy these equations for a second. Which one should I copy? Let's copy these guys. It's a lot of taps to do this. And the reason why it's taking a long time is because I have to do, like, in order to do this copying that you're seeing, it takes like 7 or 8 taps on the iPad. Okay, so here's bias variance. It's unbiased if the bias is 0, right? So if it's the case that this is equal to this, then this is going to be equal to this, and the bias is going to cancel out. We're going to get 0 here. Called it unbiased estimator. And there are many estimators that are in fact unbiased. Like let's do an example. Let's do an example of an unbiased estimator. So now we have to make certain assumptions in order to set up a problem that is an unbiased estimator, but we can do so mathematically and statistically. So we're going to start with a linear model, because right now at this point, all we know about are linear models and logistic models, which are kind of almost linear models, right? They're only nonlinear because of the logistic function. But we're starting with a linear model. So y is equal to h theta star of x, where theta star are the true parameters, right? But it's noisy, right? So that there's a little bit of random Gaussian noise added to each predictor. So the truth is really this, but the Gaussian noise is an independent Gaussian noise with 0 mean and sigma squared variance. And all that is just noise, because maybe it models our sensor, that maybe we're using a sensor and it's a noisy sensor, right? All sensors have noise. No sensors can monitor reality perfectly well. So now we're going to make the assumption that this is the true generative process for some theta star. And let's just set up, like we did the matrix version of this. We had the design matrix X and a length and column vector Y vector. And so this is the matrix representation of things, that Y vector is equal to X times theta. And you remember this picture, we had X. Here's the vector X, where each one of these guys are the X vectors, and we have theta, which is the column vector, and then Y is this thing. We saw this picture last time, right? Except we now have noise added to it, sigma, and sigma is a length n vector of Gaussians. So it's kind of like each one is just itself a separate, independent Gaussian random noise term with zero mean and sigma squared variance. So in this linear regression problem, we have already solved the normal equations, and so we can then say, well, what is the solution? Well, the solution is sigma. The optimal solution is sigma tilde, which is the Moore-Penrose pseudo inverse, which when we write everything out, is equal to, based on this data, is equal to theta star, which is the exact thing, plus this inverse, the pseudo inverse applied to this random vector epsilon vector. And this is a random vector, right? Why is it a random vector? Well, because sigma is itself a random Gaussian vector with zero mean, and each term has variance sigma squared, right? So like this is a random vector, this is a fixed value. So what we're getting, our estimate is a noisy version of truth, right? It's a noisy version of truth, or a noisy version of sigma star. Now the best estimate, the E of Y given X is equal to just truth, right? It's just sigma star transpose times X. That is the true estimator. And what we have, sigma tilde, I keep saying sigma. This is theta. I'm really sorry about this. This is theta. See, that's proof that I make mistakes. I've now given a formal mathematical proof of my own mistake-making ability that I'm calling theta sigma. And the other reason is because it's 920. But if you hear me making a mistake like this, by the way, please correct me, because, and now this will go down on record. So maybe 1,000 years from now in the YouTube archives, people will, be doing research on early 21st century machine learning course lectures and discover us learning about bias variance for the historical archives. And it will be done by people in the humanities, not in the engineering world. Anyway, so this is theta, right? So we're saying theta tilde is equal to the Moore-Penrose inverse, which is equal to the true theta star, times the inverse applied to this noisy vector, sigma vector. And the best estimate is theta star transpose times X. So what we wanted to get at is the bias, right? So here we have this error, right? So the error is broken. There's the inherent error here. There's the inherent error, which we can't reduce. And here's the error in terms of the model, which we can break in terms of our variance plus bias squared term, right? This is equal to variance plus bias squared. Now let's see, what is the inherent error? So the inherent error is just the expected value of the best predictor minus Y. We have the best predictor right there. We can actually look at it. And the best predictor is just this term, which is this term. But that's just going to be, when we do, we have an expression for Y, right? Y is equal to the best predictor plus sigma again, or sigma plus epsilon. Y is equal to the best predictor plus epsilon. the best predictor is this. When we take the difference, this whole thing is just going to be epsilon. And epsilon is a vector that has, zero mean and variance sigma squared. And so this whole term here is just going to be sigma squared, right? So that means that the only way to drive this down is to change the problem, right? But the noise, so one way we could drive it down is to improve our sensor, but that, like the sensor, improving the sensor isn't really a machine learning problem. That's a physical hardware device physics problem. That is not our problem. Our problem is, given the sensors that we've got, try to do the best job at designing and producing a machine learning system. So in this particular case, we've got the bias plus variance term there, right? So we have theta tilde, right? Remember what theta tilde is? Let's do this mode here so we can see both slides at the same time. Right, so we have theta tilde up here, which is equal to theta star, the best theta, plus this random, this is the effect of the random noise on the model, right? Which is different than the overall inherent error. This is the effect of the random noise on the model, which is that we have the true parameters plus some noise. And so the expected value on different data sets will be the following. But the different data sets, this whole thing here, when you think about this whole thing, this is a linear transformation of a Gaussian, right? And so this therefore becomes, and since the Gaussian has got zero mean and a particular variance, the mean of that linear transformation of a Gaussian is also going to be zero. Because anytime you take a linear transformation of a Gaussian, you still have a Gaussian. And if you have a linear transformation of a zero mean Gaussian, because it's a linear transformation, you're not changing the mean. I mean, you might change the dimensionality, but there's nothing, the expected value. The reason why is like whenever, let's say that X is a Gaussian random variable. And let's say that A is a matrix. Let's say X is a normally distributed random variable with zero mean and some sort of sigma squared. And whenever you have like, this is the scalar case. Let's just do the scalar case for a minute. So like when we have alpha times X, where alpha is the scalar, we have the expected value of alpha times X is equal to alpha times the expected value of X, which is equal to 0, because E of X is equal to 0. And so it's the same thing here, except that this is just the matrix version of it. So what we have therefore is an unbiased sample, because when we take the expected value of this learned model, we have it equaling to the true model. So the mean is really good, it's unbiased. The bias is 0, and here's the bias squared, right? So the bias term is 0. The variance, and this is a really important equation, the variance is not 0. The variance is something that depends, first of all, let's look at what the variance is again. The variance is equal to the expected value of, this is with respect to D, the training data set, of H of dx, minus the mean of the estimator, quantity squared, and then taking the expected value over D. And with a little bit of algebra, we can show that the variance is actually equal to this expression. So the variance, first of all, is going to be related to the sigma, the same sigma that produced the noise, that is our representative of the sensor measurements. But the variance is going to get worse with the dimensionality of X, right? So remember we said that X was a vector in Rm. So for very, very high dimensional inputs, our variance is going to get worse. But we can improve that by increasing the data set size. Remember, n is equal to the number of training samples. So one way of reducing the variance is by decreasing the training size. Now, this is something that's really important in machine learning, right? You've heard the expression, there's no data like more data. Generally speaking, what the effect of having more data is that if you were to treat your training data as a random sample from the data set random variable, you can, one of the problems, like you might have some data and you train up your deep model, you train up whatever model you have, and it does quite poorly. And no matter what you do, it does terribly. You've tried this, you tried that, you try all the latest techniques, you've taken this class, you're an expert in machine learning, and no matter what you do, it just doesn't work. It could very well be because you just got unlucky and you got a data set that's not really representative of the true problem. If you have a larger data set, the probability of having a data set that's not representative of the true problem decreases. And that's because, again, because of the law of large numbers and those kinds of limiting properties, it becomes less and less probable for large data sets to be unrepresentative of the true distribution, and becomes more and more probable that small data sets are not representative of the true problem. And one of the reasons, by the way, like what I always say, like, why have we experienced such massive improvements in machine learning and artificial intelligence over the past decade? And one of the reasons is that the data set sizes have just gotten a lot bigger. And we have greater storage capacity, and we have greater computational capability that can deal with such large data sets the size of which weren't possible to deal with in earlier days of machine learning. So in some sense, the same general ideas, the same techniques that people in machine learning have been working on for decades still kind of work. It's just that they didn't have enough compute and they didn't have big enough data sets. And that is itself kind of remarkable, that you have folks who worked on this stuff in the 60s and the 70s and then died and never got to see that what they were doing was correct. That they saw failure after failure after failure, but they just didn't have enough compute and they had too small data sets. So that's kind of interesting. So anyway, so this is sort of like a mathematical demonstration of the benefit of larger data sets, which is namely saying, in this particular case, that the variance of your model is going to be small. The variance of your learned model is going to be small. So it's very unlikely. If the variance is small, it's very unlikely that you're going to get some data set that's going to produce a model that's going to be aberrational, that's going to be unusual or different than everybody else. That no matter what data set you choose, you're always going to get pretty much the same answer. That's what low variance means. Now, one thing in particular I want to say also is that there's a famous theorem in machine learning, the Gauss-Markov theorem, which says that, first of all, amongst all unbiased estimators, the linear least squares estimator, even irrespective of the data set, before we actually worry about too big data sets, like how do we decrease the variance? Generally simple models are preferred because they have lower variance. And in fact, the linear least squares has the smallest mean squared error amongst all unbiased linear estimators. So in other words, the variance of theta according to a linear least squares model is less than or equal to the variance of any unbiased estimator of theta. So this is pretty good. I mean, this is linear least squares model, even as simple as it is, there are already some interesting mathematical properties that we can show. Now, I'm not going to prove that theorem, but it's just something that goes to show that what we're talking about still has some mathematical benefit. Okay, so actually, that's all I had for today. That I don't have any more slides, but I want to conclude by not letting anybody go as if I have a handcuff on you. I don't leave the room until somebody else asks one more question, or at least one more question about bias variance and overfitting and underfitting.
I have another
I'm one of
question
these
then.
faculty who thinks that he has good jokes and doesn't. So if you're wondering why I keep attempting to making attempt at humors, it's because of that fact. So, but I am serious about asking for questions or waiting for questions.
Can you hear me?
I can, but I don't know who you are, and it's pretty quiet.
Oh, sorry.
Yeah, I can hear you.
Yeah, this is Brendan. I had a question about the inherent error. So if you're looking at a model and you discover that your inherent error is so large, do you just kind of like disregard the data? Like, is there a point where you say your inherent error is like way too large for it to be any good training or data set?
In it is. I mean, so it but it might not be hard. It might not be easy to know that the inherent error is too large. One of the things that makes the inherent error large. I mean, you've probably heard about that. There's if you look at real world data sets, they're incredibly dirty. Meaning, you have fields that are just wrong, and the reason why they're wrong is because these are big giant tables that came from data entry operators, and people just typing in numbers, and people typed in the wrong number, or you have missing fields, like some of the records are just gone, or some of the records are the wrong data type, and that can lead to error in your data, which can make it such that you have inherently high error, high inherent error. Let's go back to that decomposition. Let's talk about it. I think this is the slide. Right. So, I mean, in some sense, you're changing the distribution. It's often very difficult to know, and it might be the case that without doing additional experimentation, you don't really know what the inherent error is, and you don't know this until you try things. So it's kind of hard. It's because this is not really a computable thing. In the case of linear regression, in the model that we saw that the inherent error is related to the noise in the measurement, right? And there, what we can do is we can set up kind of artificial environments, like the one we just did, where we assume it's Gaussian, we assume that the noise is Gaussian, we assume that the relationship is linear, and see what are the things that determine the inherent error. And then we can go back to our data collection process and maybe look at that to see whether or not our data collection process is very, very noisy. Like let's say you design some new sensor or something, and then you're working for some company that does some kind of room sensor, and it detects, I don't know, the number of people in the room, because you have automated smart home windows that start circulating air at a higher rate depending on its estimate of the number of people that happen to be in the room, right? Which is the typical kind of smart home device that you might see advertised at CES these days. So you have this sensor which detects the number of people in the room, and you might then just at the very beginning come up with an estimate of the noise of the sensor. And you do that by looking. You say, okay, well, I've got 20 people in the room, and this sensor says it's 25 people, and I've got 10 people in the room, and this sensor says it's 3 people. And if you have that, if the sensor is that noisy, you might say come up with a model that estimates the sensor with that degree of noise, and then derive mathematically an estimate of the inherent error. It's never going to be perfect, but you can kind of estimate the noise of a given sensor or a collection of sensors, and then come up with an estimate using, Gaussians are very useful for this kind of thing, because oftentimes the noise, Gaussians are a reasonable model for many different noise sources, and come up with an estimate of the inherent error. But getting the actual inherent error in getting this quantity it's unobtainable. It's just not something we can compute exactly, because we don't have p of x comma y. Nor do we know what this is. There's a lot of things we don't know, but we know it exists. I mean, assuming if you allow for the fact that data is generated by a random source, we know this exists. And so, I mean, it sounds like you're asking a very rational and practical question, which is, well, how do you deal with it? I mean, the way you deal with it is by being aware of it and being aware that it might be a problem. And when you're looking at a particular machine learning problem, you have to constantly be thinking. I mean, whenever I see a new machine learning problem where people are applying any machine learning technique, whether it's deep model or otherwise, I'm constantly thinking personally about bias variance. And could the problem be a bias problem? Is the data set too big? Is it too noisy? Where could things be problem? It's the inherent errors. There's also something that we're going to be talking about called Bayes error, which is kind of like a light speed for error for certain classification problems. We'll be talking about in the next week or so. There are other kinds of things you have to be thinking about, like maybe you've come up against these inherent limits.
Yeah, it's like a case by case thing, right?
It's a case by case thing, exactly. And you just the answer to your question is you have to be mindful of these phenomena. You have to understand them first of all, be mindful of them, and be skeptical and suspicious of your machine learning models, and kind of probe them and try to see what about them can you try to discern by the process of experimentation. Like, one way you could try decreasing the data set by a quarter, or you could try sampling the data set. We're going to talk about techniques like boosting and bagging and those sorts of methods where you do subsamples. And sometimes what you can do is you can pretend you have less data than you actually have. You can never pretend, or it's often hard to pretend you have more data than you actually have, but sometimes you can pretend you have less data. And if you see that you're getting wildly different model estimates, then well, you know very little. But on the other hand, if you see that if with a quarter of the data you're still getting exactly the same model, then you know it's probably not a variance problem for all of the data that you've got, because you're getting low variance even for less data. So you can do sort of one-sided ruling things out, where the result of the experiment it will either tell you nothing or something.
I see.
But yeah, that's a good question. Okay, how about one more question? I can answer, I see on the chat that the difference between EP and ED is still there. I can answer that one again.
So does this idea of variance and bias apply to all models essentially? So is this like a generalized, or is this more specific to linear least squares or regression, logistic regression?
It applies to every model. Anytime you're doing, whether it's a deep model or support vector machine or decision tree or boosted, gradient boosted decision tree or whatever, it applies to everything. The one context where bias and variance, the bias variance trade-off kind of may not immediately apply is when you're doing Bayesian analysis. And Bayesian analysis is something that we'll touch on a little bit later in the class. And one of the arguments in favor of Bayesian analysis is that things like bias and variance may be something that's something that doesn't come up in those contexts. But one of the problems with Bayesian analysis is that it has its own impracticalities. So that in practical real world machine learning systems, usually you don't really have, I mean, it's like it requires more assumptions to get rid of other assumptions. So like it comes with its own other collection of things that you can't estimate. So for most practical machine learning systems, folks usually don't use Bayesian analysis, but we will mention that in that context. I mean, in part of this class, I'm trying to, on the one hand, we want to try to, as much as possible, understand the mathematical properties of things, but at the same time, I kind of expect that most of you, are here because you also want to learn about, how do you get this stuff to work, in practice, and so we're sort of we're trying to sort of, I'm trying to be mindful of that, but at the same time, you should also be tolerant of the fact that we're going through a lot of the mathematics of it, and really work hard on it, because it's really valuable. If you work hard on understanding the mathematics behind something, it's going to help you a lot in practice. There's no escaping math. So, other questions?
I might have a question. Can you hear me?
Yep.
Okay, so I'm still trying to figure out the expected value, and honestly, right now I'm just trying to figure out what I don't know, so I can ask the question, you know. So, with the expected value, well, let's see if you can answer this for me. In any case where we're doing the p of y given x, that is going to be something that we can't know for certain, right?
Yeah, so p of y, any of these things, so any, p of x comma y, p of y given x, or p of x, any of these guys, we don't really know. We don't have access to these other than through the process of collecting data sets. We can get information about them, and the larger the data we have, the more information about these guys we've got. But we can never say, I've got this. It's not like, it would be great if the data came to you packaged as a probability distribution, but it doesn't, unfortunately.
So when we're working with error and we're finding the expected value with respect to p of x comma y, I guess I'm having a hard time seeing how we are going to work with that if that's something we can't know. I'm probably not thinking about this in the right way.
Well, think about it this way. So like, let's say, let me just do a brief description of like the law of large numbers. So let's say let's say that x is some random variable, right? So x is and so we have x as a random variable, and let's forget about y for a minute. Let's just say it's a single random variable x, and you've got p of x, right? So this is the distribution for this random variable. And what you want to do is you want to compute the expected value of x, right? And what the expected value of x is the integral of x of p of x, b of x, right? This is the thing we want to compute, right? But there's several problems with computing this expected value, which is one, that we need to have p of x, and the other is that we need to compute this integral, and computing that integral might be very complicated and costly. Right? So what we can do instead, and this is sort of a sampling, sometimes it's called Monte Carlo methods, but basically what we do is we take some data sets, and this is just a sample data set, and this is and it's just basically x of I, where I is equal to 1 to n. We're assuming that x of I is sampled according to p of x, right? So each one of these is a sample of this random variable. And we saw this in the case of coin flipping, right? So like, we want to be able to, we want to know what the bias of a coin is, but we don't actually have the access to the true probability of heads versus tails. But we can flip the coin a bunch of times and count the number of heads divided by the total number of flips. And that gives us an estimate of the probability of heads. It's not perfect, but the bigger the number of times, the larger the number of times that we flip the coin, the better the better accuracy we get. Now, with respect to computing this expected value, instead of this, what we can do is come up with some estimate. The expected value of x is approximately equal to the sum for I is equal to 1 to n of x of I. Right, and it's just taking the average, and so the average, it's just the average of the sample, and so we can't, we can't compute this exactly, but we have that this guy, as n goes to infinity, as the data set gets larger, approaches the expected value of x, approaches the quantity that we care about, right? So it's just taking the expected value. This is the empirical expected value. This is the actual expected value. So the bigger the sample set we get it. So while we don't have access to this, we can get access to quantities that we care about.
Okay.
Right.
So that the expected value there, if we had a distribution that looked like just a normal Gaussian, the expected value would be finding the peak of that Gaussian?
Yeah, it's the mean in this case. So the mean happens to be the peak. The peak is officially the mode, but in the Gaussian case, the mode is equal to the mean.
Okay.
Which is the peak, which is the same as the peak.
Okay,
the
so
location,
if it was just
it's the location of the peak. The location.
Okay. if it was a flat distribution, it would find the center of the distribution.
If it's a uniform distribution,
Yeah.
so if it looks like this, then
Yeah.
the mean will be in the center, right?
Okay. Yeah, that equation looks a lot like I think center of mass.
It's exactly center of mass. It's exactly the same
okay.
equation. In fact, you can think of the center of mass. I mean, when you compute the center of mass, the thing that is analogous to probability is mass density, right? So when you take the integral, when you're trying to compute the center of mass, you're taking the integral where what you're taking x is like all positions in space, right? It could be in 1 dimensional, 2 dimensional, 3 dimensional, but it's like you've got the coordinate, which is x, and then you've got the mass, the sort of instantaneous mass density, which is kind of like p of x, right? X is the coordinate, p of x is the mass density in the center of mass, because the center of mass isn't necessarily, you know, like if it's perfectly uniform object, and if it's a rectangular block, the center of mass will be right in the center in this way. But what if you have a rectangular block which has variation in mass density? So it's no longer the volume, it's the mass density that matters. And so probability is analogous to mass density.
Okay. Okay, I think I'm starting to understand how we could be working with that a little bit more. Oh, is there anything else that you'd like to?
No, I'm just giving folks opportunities to ask questions. Otherwise, if nobody has any questions, we can drive home in the snow. But actually, Chandrasekhar and Niraja, I wanted to Zoom with you guys for a few minutes afterwards to talk about the problem set, because I want to get that out soon. And somebody asked, when we're going to have the video posted? I want to get it out there ASAP. So I'm going to try to get it out there tonight, depending on how cooperative Zoom is with me. So, and I think it takes a while for Zoom to do the conversion. And that also depends on the laptop speed and everything, but I'll try to get it out tonight, unless it actually finishes at 4 in the morning, in which case it'll be tomorrow morning sometime. Okay, I think that's good. I think we're good, and I hope everybody enjoyed our Zoom lecture. Next Tuesday, unless it's snowing, we'll be back to our usual location and place. And enjoy the snow, enjoy the rest of your week, and stay safe out there, and don't slip. Bye, everybody.